Hello and welcome to this revision session for AQA A-Level Physics Paper 2 on the topic of thermal physics. So if we've been successful and we've learnt in today's revision session, we should be able to answer A-Level Physics examination style questions, assess our understanding on A-Level Physics and understand what topics we need to improve upon for A-Level Physics. So how should you prepare for this revision session? When you're completing this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than on the right hand side. In this section, please ensure you write down your working out answers to the questions in your revision session. When you're doing this, make sure you write in full sentences and show your full working out. Whilst in the right hand side, write down any bits of information which you find useful or any hints and tips on answering questions from this revision session. After the end of the revision session, write up these notes into a revision sheet for you to use independently. So how should you be revising for your A-Level Physics? So the first step is to learn the key facts. Use revision guides, class workbooks, student prep notes and the textbooks to learn the key ideas of the course. Now you may wish to make mind maps or to write out notes yourself. Then test yourself. Use things like Caboodle, Seneca, student knowledge checkers to quickly test your own knowledge, and you may wish to do this from your own cue cards. Then use exam preparation books, homework books, supervised study books, additional workbooks to answer examination questions and mark your own work, and you may wish to download your own exam past papers to do this. So learn the key facts, test yourself, and practice exam style questions. So what are the key facts to do with thermal physics? Well, in thermal energy transfer, we know that the internal energy is the total kinetic energy and potential energy of the particles in a system. We know that internal energy will increase when heat is transferred into the system or work is done on the system. So the change in internal energy is equal to the energy added as heat plus the work done on the system. Now, during a change of state, the potential energy changes, but the kinetic energy remains constant. This leads to no temperature change. Now this means the energy required to cause a temperature change is equal to Q equal mc delta theta, whilst the change of state, which is linked to the latent heat, is equal to Q equals ml. Now for ideal gases, we know the gas laws are Boyle's law, which is where P is proportional to 1 over V at constant temperature, and Charles's law, which is V is proportional to T at constant pressure. Now absolute zero is a theoretical temperature at which particle motion will fully cease. Now our ideal gas equations are PV equals nRT for moles and PV equals nKT for molecules. Now the work done by a gas is equal to the work done equals the pressure times by the change in volume. You must be aware of the molar mass and the molecular mass, and then how to use Avogadro's constant. Now in terms of molecular kinetic theory, Brownian motion provides experimental evidence for the existence of atoms, the irregular motion of smoke particles under a microscope caused by unseen gas molecules. You must be able to link P, V and T to microscopic behaviour, so it explains macroscopic gas laws using a molecular model of particles in constant random motion. Now, the gas laws are empirical based on observations, whilst the kinetic theory derives relationships from first principles using physical assumptions. Now, the internal energy of an ideal gas is the total kinetic energy of its molecules only. There is no potential energy. Now, again, scientific models evolve, so understanding of gases has changed over time due to experimental evidence and theoretical development. Now, the kinetic theory equation is PV equals 1/3 nm root mean square velocity squared. So the average molecular kinetic energy is a half mc RMS squared, which is equal to 3 over 2 kT, which is equal to 3 RT over 2 Na, or Avogadro's constant. Now, the assumptions of the kinetic model are that the particles are point masses, all collisions with walls in between molecules are elastic, there's no intermolecular forces except during collisions, the time of collision is negligible, motion is random and isotropic, it's the same in all directions, Newton's laws apply to the motion of the gas molecules, and there's a large number of molecules present. So let's have a look at some general check questions to do with thermal physics. So, what is meant by the term internal energy in a system? Internal energy is the total of the randomly distributed kinetic and potential energies of all the particles found within a body. How does heating affect the internal energy of a substance? Heating increases the internal energy of a substance, normally by increasing the kinetic energy of its particles. So what are the two ways in which the internal energy of a system can be increased? Internal energy can be increased by heating the system or by doing work onto the system, such as compression. During a change of state, what happens to the internal energy of the substance? Well, internal energy will increase because the potential energy of the particles changes, even though their kinetic energy stays the same. Why does temperature remain constant during a change of state despite energy being transferred? Well, because the energy is going into changing the potential energy store, which will be either breaking or forming bonds or intermolecular forces of attraction, not into increasing the kinetic energy. What is the equation used to calculate the energy needed to change the temperature of a substance? Well, Q equals mc delta theta, where Q is energy, m is mass, c is specific heat capacity, and delta theta is the temperature change. What does the specific heat capacity of a material tell you? It tells you the amount of energy needed to raise the temperature of 1 kilogram of a substance by 1 degree Celsius or 1 Kelvin. What equation is used to calculate the energy required for a change of state? Q equals mL, where L is the specific latent heat and m is the mass of the substance. What is meant by the term specific latent heat? It is the amount of energy required to change the state of 1 kilogram of a substance without a change in temperature. What is meant by continuous flow in thermal energy calculations? It often refers to scenarios where a fluid flows steadily through a system, often requiring ongoing heat transfer calculations based on the mass flow rate present. What is the relationship described by Boyle's law? Boyle's law states that for a fixed mass of a gas at constant temperature, the pressure will be inversely proportional to the volume. P is proportional to 1 over V. What does Charles's law state about the volume and temperature of a gas? Charles's law states that for a fixed mass of gas at constant pressure, volume will be directly proportional to absolute temperature. V is proportional to T. What is meant by the term absolute zero? Absolute zero is the theoretical temperature at which all particle motion ceases, and the internal energy is a minimum and it is only potential energy. It's equal to 0 Kelvin or minus 273.15 degrees Celsius. Write the ideal gas equation for a fixed number of moles. The ideal gas equation is PV equals nRT, where P is pressure, V is volume, N is moles, R is the molar gas constant, and T is the temperature in Kelvin. What is the alternate form of the ideal gas equation using number of molecules? Well, PV is equal to nKT, where N is the number of molecules, K is the Boltzmann constant. What is the equation for work done by a gas during expansion or compression? Work done is equal to P delta V, where P is the constant pressure and delta V is the change in volume. What is the significance of the Boltzmann constant K in the kinetic theory of gases? It relates the average kinetic energy of a gas particle to the absolute temperature, and it's used in the equation PV equals nKT. How is the molar mass of a substance related to its molecular mass? Molar mass in grams per mole or kilograms per mole is the mass of 1 mole of a substance and is numerically equal to the molecular mass in unified atomic mass units. What does the Avogadro constant represent? It represents the number of particles, atoms or molecules in 1 mole of a substance, and it's approximately equal to 6.022 times 10 to the 23. What does Brownian motion provide evidence for? Brownian motion provides evidence for the existence of atoms and molecules, as it shows particles being moved by invisible collisions with smaller particles. What does the kinetic theory model aim to explain? It explains the relationships between pressure, volume, and temperature of a gas using a theoretical model based on molecular motion. How do the gas laws and the kinetic theory differ in terms of origin? Gas laws are empirical. They're based on experimental observations, whilst the kinetic theory model is derived from theoretical assumptions. What assumptions are made in the derivation of the kinetic theory equation for an ideal gas? Particles are in random motion. The collisions are perfectly elastic. The volume of the particles is negligible, and no intermolecular forces act except during collisions. For an ideal gas, what is the internal energy equal to? The internal energy is equal to the total kinetic energy of the gas molecules. How is the average kinetic energy of a molecule related to its absolute temperature? It is directly proportional to temperature. As T increases, the average kinetic energy of the molecule increases linearly. What does the term CRMS refer to in the context of gases? It refers to the root mean square speed, a measure of the average speed of gas molecules accounting for their squared velocities. Why has the understanding of gas behaviour improved over time? Because scientific knowledge and technology has advanced, allowing for better models, better measurements and better observations of particle behaviour. For an ideal gas, why is internal energy considered to be only kinetic and not potential? Because in the ideal model, there are no intermolecular forces of attraction between the particles, so particles do not have a potential energy stored due to their position. Let's now have a look at a few questions concerning thermal physics. A cryogenic fuel tank on a spacecraft contains 2 kilograms of liquid oxygen at its boiling point of 90 Kelvin. During a test, a heater supplies energy at a constant rate of 120 watts to the tank for 600 seconds. The tank is well insulated and no oxygen escapes during the test. The specific latent heat of vaporization of oxygen is 2.13 times 10 to the 5 joules per kilogram. The specific heat capacity of gaseous oxygen is 920 joules per kilogram per Kelvin. Calculate the total energy supplied by the heater. Determine the mass of the oxygen that changes state from liquid to gas during the heating process. Explain why the temperature of the oxygen remains constant during the 600-second heating period. Then an engineer suggests that the temperature of the oxygen should have risen steadily from the start of the heating. Evaluate this suggestion. So, pause the video now, then unpause the video when you want to go through your answer. Right, we know the energy supplied is power times by time, so we work that through with 72,000 joules. Now the energy required to vaporize all 2 kilograms is E equals ml, and we said m to 2, so it's 426,000 joules. So what we can therefore say is that the mass vaporized is going to be m is equal to q over l. So therefore it's 72,000 over 2.13 times 10 to the 5, which is 0.338 kilograms. So it indicates to us that unfortunately we haven't been able to vaporize all of it. Now, not all of the liquid oxygen will vaporize. All energy therefore is being used to break intermolecular forces of attraction or bonds during this phase change, so the temperature remains constant at 90 Kelvin during this process. Finally, the engineer's suggestion ignores the latent heat of vaporization. The temperature cannot rise until all of the liquid has fully vaporized. A distillery uses a copper heat exchanger to condense ethanol vapor at 78 degrees Celsius into liquid ethanol. Cold water flows continuously through a coiled copper pipe to absorb the energy transferred as the ethanol condenses. The ethanol vapor enters the heat exchanger at 78 degrees Celsius and exits the liquid ethanol at 78 degrees Celsius. The mass flow rate of the ethanol vapor into the condenser is 0.050 kilograms per second. The specific latent heat of vaporization of ethanol is 8.5 times 10 to the 5 joules per kilogram. The water enters the coil pipe at 12 degrees Celsius and leaves at 48 degrees Celsius. The flow rate of the water is 0.120 kilograms per second, and the specific heat capacity is 4,200 joules per kilogram degree Celsius. Explain why the temperature of the ethanol does not change during condensation, even though the energy is being transferred out of the ethanol. Calculate the rate at which energy is transferred from the ethanol during condensation. Then calculate the rate of energy gained by the cooling water. Compare your results and suggest one possible reason why they might not match. If we decrease the flow rate of water, it will cool the ethanol more effectively because it will get hotter. Evaluate this claim. So, pause the video now, then unpause the video when you want to go through your answer. In our first one, energy is transferred out to overcome the intermolecular forces of attraction during phase change. Now the potential energy of the particles decreases, but the kinetic energy and therefore the temperature must remain constant. We can work out the energy transferred from the ethanol by doing Q equals ml, and we get 42,500 watts, or joules per second when we work this through. The temperature change is therefore going to be 36 degrees Celsius, so the energy gained by the water is mc delta theta, or 0.12 times by 4,200 times by 36, which is 18,144 joules per second, or watts. So for comparison, there's a difference of 42%. Now the possible reason is that not all of the energy is transferred to the water. There's losses to the surroundings, incomplete heat transfer, and the ethanol might not fully condense at the stated flow rate. Finally, lowering the flow rate causes a greater temperature rise in the water, but less mass per second of the water means that less total energy is absorbed per second, so therefore the energy transfer rate may actually decrease, so the claim is actually incorrect. A sealed high-altitude research balloon contains helium gas and is released from the ground where the temperature is 290 Kelvin and the pressure is 1 × 10 to the 5 pascals. The balloon has a volume of 2 meters cubed at launch. As it rises, the external pressure drops and the temperature decreases. At a certain altitude, the external pressure is 2.5 × 10 to the 4 pascals and the temperature is 230 Kelvin. The balloon is designed to expand freely and remain in thermal equilibrium with its surroundings. Assume helium behaves as an ideal gas. Calculate the volume of the balloon at this altitude. The balloon is fitted with a pressure sensor that records a sudden increase in internal pressure even though the external pressure continues to fall. Suggest a possible explanation for this observation. Then an engineer claims that the work done by the gas as it expands is equal to the product of the final pressure and the change in volume. Evaluate this claim in the context of the balloon's ascent. So, pause the video now, then unpause the video when you want to go through your answer. In our first answer, how can we work out the volume of the balloon? Well, we can say that V2 is equal to P1V1T2 over P2T1, so it's just using the gas laws. Pop in all the values and we get 6.34 meters cubed. Next one, a sudden pressure will increases that there's going to be a heating or compression. Now, a solar heating or the balloon reaching the elastic limit could cause an internal compression. Now, the ideal gas law assumes equilibrium conditions, and that may not apply during the rapid changes. Finally, W equals P delta V is only valid if the pressure of the gas remains constant. In this case, the pressure changes continuously during the ascent, which therefore means that it can't actually be used in this context. A student investigates how the pressure of a fixed volume of gas changes with temperature. They trap a small amount of dry air in a sealed rigid container and measure the pressure at various temperatures. The graph below shows the pressure P against the temperature theta in degrees Celsius. Explain how this experiment demonstrates the concept of absolute zero. In your answer, refer to the behavior of the particles in the gas. Use the data to determine an experimental value for absolute zero in degrees Celsius. State and explain one reason why the value obtained in A1.2 may not be exactly equal to the accepted value of minus 273 degrees Celsius. So, pause the video now, then unpause the video when you want to go through your answer. Right, in our first question, what's happening at absolute zero? Well, as temperature decreases, the pressure will decrease, indicating that particles will have less kinetic energy. At absolute zero, the particles have the minimum possible energy and exert no pressure whatsoever. So extrapolating the pressure-temperature graph to zero pressure estimates the temperature at which the molecular motion stops. So we would work out the gradient, so we would do 35 over 100, which is 0.35 kilopascals degrees Celsius. We can use the equation of the line where we get y equals mx plus c. So we can say that p equals 0.35 theta plus 100. So we set p to equal 0, because we know at absolute zero the pressure is equal to 0. Pop that in and we get theta to be coming out to be minus 285.7 degrees Celsius. Right, and that last one, air is not an ideal gas. Real gases deviate from ideal behaviour, especially at low temperatures. And in addition, we're extrapolating beyond the measured temperature range, which introduces an uncertainty into the calculation. Now, there could also be experimental errors, such as leaks, non-uniform heating, and instrumental calibration issues, which could also affect our result. A vacuum chamber is slowly filled with a monoatomic ideal gas. The gas is initially at a temperature of 300 Kelvin and reaches a pressure of 1.20 times 10 to the 5 pascals when the volume is 0.050 meters cubed. The total number of gas molecules in the chamber is 1 times 10 to the 23. Calculate the root mean square speed of the gas molecules in the chamber. The molecular mass of the gas is 0.020 kilograms per mole. The calculated root mean squared speed differs from the value predicted using the ideal gas equation. Suggest two reasons for this discrepancy and explain why this doesn't necessarily contradict the ideal gas model. Then a student claims that increasing the temperature of the gas will increase the pressure because the molecules hit the wall harder. Evaluate this claim. So pause the video now, then unpause the video when you want to go through your answer. In our first answer, we can work this out by using the equation m is equal to molar mass over the Avogadro's constant. So we pop that through and we get 3.32 times 10 to 26 kilograms. We know that C RMS is equal to square root 3 PV over nm. We pop in all the values and we get 516 meters per second. Now, the kinetic theory and ideal gas equations are based on different assumptions or simplifications. Now, real gas effects such as intermolecular forces, non-zero particle volume will affect the result. In addition, experimental or measurement uncertainty can also cause this. So there's two possible reasons. Now, finally, increasing the temperature increases the average kinetic energy. This leads to more frequent and more forceful collisions with the container walls. A sealed container of fixed volume contains nitrogen gas at a temperature of 300 Kelvin. The number of nitrogen molecules in the container is 6 times 10 to the 23, and the mass of one nitrogen molecule is 4.7 times 10 to the minus 26 kilograms. Calculate the total kinetic energy of the gas molecules in the container. Explain how the molecular kinetic theory model accounts for the pressure exerted by the gas on the walls of the container. Discuss two assumptions made in the molecular kinetic theory model of an ideal gas. For each assumption, explain how the behaviour of a real gas may differ from the ideal case. So pause the video now, then unpause the video when you want to go through your answer. In our first one, we can say E is equal to 3 over 2 kT. That's the kinetic energy of the gas molecules. So you pop it all through and you get 3.73 times 10 to the 3 joules. Now, molecules will move in random directions with a range of speeds. So the molecules collide elastically with the container walls. So each collision will change momentum as they change in direction, so it exerts a force on the wall. The pressure is then due to the net force from all the molecular collisions over the container surface area. Now, the ideal gas assumes no intermolecular forces. Real gases do have attractions, especially at a high pressure or low temperature. The ideal gas also assumes that molecules occupy a negligible volume. Real molecules do actually occupy a space. In the early 19th century, gas laws such as Boyle's law and Charles's law were discovered experimentally. These laws described how the pressure, volume and temperature of gases were related, but provided no explanations of why gases behave this way. Later, the development of the kinetic theory model and the observation of Brownian motion helped scientists to understand the microscopic behaviour of gases. Describe how the observation of Brownian motion provided evidence for the existence of atoms or molecules. Explain why the gas laws are described as empirical and how the kinetic theory model provides a theoretical explanation of gas behaviour. Then discuss how our understanding of the behaviour of gases has changed over time, referring to both experimental evidence and theoretical developments. So pause the video now, then unpause the video when you want to go through your answer. Right, in our first question, we can say that Brownian motion refers to the random movement of visible smoke or pollen particles suspended into air or fluid. The motion is caused by collisions with much smaller invisible gas or liquid particles, atoms or molecules, so this provides indirect evidence for the existence of motion of individual atoms or molecules. Now, the empirical laws are based on observed experimental relationships. For example, P is proportional to 1 over V at a constant temperature. These laws are describing what happens, but not why. The kinetic theory model is based on theoretical assumptions about particle motion and collisions, so it does explain gas behavior in terms of microscopic motion and the energy of gas particles. Now, early models treated gases as continuous substances with no understanding of their microscopic structure, that they were made from particles. Experimental observations, like Brownian motion, supported the idea that they were made from particles. The kinetic theory introduced a model that explained pressure and temperature in terms of molecular motion and energy. Over time, quantitative predictions align with the theory with the experiment, leading to widespread acceptance. 50 years ago, Henri Peterie developed a device for the kitchen that produces instant boiling water. A modern version is shown. The system consists of a small tank connected to the water supply. Water in the tank is heated under pressure to a temperature of 110 degrees Celsius. When the water flows out of the tap, the temperature falls to 100 degrees Celsius. Water enters the tank at a temperature of 12 degrees Celsius. An electric heater increases the temperature of the water to 110 degrees Celsius. The water does not boil because it is under pressure. Calculate the time taken to heat a full tank of water to 110 degrees. So, pause the video now, and then unpause the video when you want to go through your answer. Right, in our first one, what we can say is E is equal to P times by T. So therefore T is equal to E over P, and we know E is equal to mc delta theta, and P is equal to Vi. We know mass is equal to density times by volume, because you're given the density and the volume in the question. So you can pop in all the values and work it through. Now remember, delta theta is the change in temperature. So you pop in all the values and we get 423 seconds. The next question says that when the water flows out of the tap, the temperature falls to 100 degrees Celsius. The average rate of energy transfer from the tank to the surroundings is 9.5 watts. A full kettle contains 1.4 times 10 to the minus 3 meters cubed of water. It takes 180 seconds to bring a full kettle of water to 100 degrees Celsius. The kettle is used to bring enough water for 28 cups of tea to 100 degrees Celsius. A reviewer compared the energy transferred from the tank to the surroundings in 24 hours with the energy transferred by the kettle to make the tea. A reviewer claimed that the energy transferred from the tank will be greater than the energy transferred by the kettle. Assess the validity of this claim. So, pause the video now, then unpause the video when you want to go through your answer. Right, in answering this question, we can work out the energy transferred from the tank, which we know is P times by T. So from the information given, and we're told that's in 24 hours, so we convert our hours into seconds, we get our answer to be 8.21 times 10 to the 5 joules. Now we can also then work out the volume needed for 28 cups of tea. So it's 28 times by 3.5 times 10 to the minus 4. So it's 9.8 times 10 to the minus 3 meters cubed. Now the number of kettles required will be that value divided by the capacity of one kettle, which is 7. So the time for the kettle to be switched on is 7 times by 180 seconds, because we're having 7 of them and they've got to be on for 180 seconds each at a time. So that's 1260 seconds. So the energy transfer to the kettle is power times by time, which is 3.28 times 10 to the 6. So what we can say is that 3.3 times 10 to the 6 joules is greater than the energy provided, which is 8.2 times 10 to the 5 joules. So our claim just is not valid. The next question says ice cubes can be made in an ice tray. One type of ice cube tray is shown. Each compartment in the ice cube tray has dimensions of 2.5 centimeters by 2.5 centimeters by 3.5 centimeters as shown. Show that the mass of the water needed to fill one compartment is about 0.020 kilograms. All 6 compartments in the ice cube tray are filled with water to a depth of 3.5 centimeters. The ice cube tray is placed in a freezer. The initial temperature of the water is 22.5 degrees Celsius. It takes 12 minutes for all the water to become ice at 0 degrees Celsius. The manufacturer of the freezer states that the freezer can transfer energy at a rate of 110 watts. Evaluate whether the energy is transferred from the water in the tray at a rate of 110 watts. So pause the video now, and then unpause the video when you want to go through your answer. In our first question, we would say density is mass over volume. So therefore, we can say volume, we can work it through to be 2.5 times 10 to the minus 2 times squared times by 3.5 times 10 to the minus 2, which is 2.2 times 10 to the minus 5, or meters cubed. So therefore, we can then pop that in and say mass is going to equal to density times by volume. We've got our density, we've got our volume, so our mass is 0.0219 kilograms. We know the energy needed to change temperature is E is equal to mc delta theta. We pop in all the values. Remember, our delta theta is the change in temperature, so it's 22.5 Kelvin. So therefore, it's 1.224 times 10 to the 4 joules. The energy required to change state as it freezes is ml. So we pop that in and we work the answer through to be 4.41 times 10 to the 4 joules. Now remember, in both cases, there are 6 ice cubes, so you've got to multiply both values by 6. Now the power is equal to the energy divided by the time. Now the total energy is both the energy stored from the latent heat, which is the potential, plus the energy stored from the kinetic, which is the specific heat capacity one. Add the two together, divided by the time, which is 12 times by 60. So then we can work it all through, because it's 12 minutes, we want it in seconds. So we get our answer to be 78.5 watts. So that brings an end to our revision session today. If we've been successful and we've learned in today's revision session, we should be able to answer A-Level Physics examination style questions, assess our understanding on A-Level Physics, and understand what topics we need to improve upon for A-Level Physics. So thank you so much for watching this revision session on AQA A-Level Physics on the thermal physics topic, which is part of paper 2. Thank you so much for watching and have a lovely day. Hello and welcome to this revision session for AQA A-Level Physics Paper 2, looking at the topic of thermal physics. So in today's revision session, we're going to look at how to answer examination questions on A-Level Physics Paper 2. So if we've been successful and we've learned in today's lesson, we should be able to answer A-Level Physics examination style questions, assess our understanding on A-Level Physics, and understand what topics we need to improve upon for A-Level Physics. So how should you prepare for this revision session? When you're completing your work in this revision session, divide your piece of paper into 2 sections. Make the section on the left hand side larger than the right hand side. In this left hand side section, write down your working out and answers to the question in the revision session. When you're doing this, make sure you write in full sentences and show your full working out. Whilst in the right hand side, write down any piece of information which you find useful or any hints and tips on answering questions from this revision session. After the end of the revision session, write up these notes into a revision sheet for you to use independently. So how should you be revising for A-Level Physics? So the first thing to be doing when you're revising independently for A-Level Physics is learn the key facts. Use the revision guides, the class workbooks, the student prep notes, the textbook to learn the key ideas of the course. You might wish to make mind maps or to write out notes yourself. The second step is to test yourself. So use things like Caboodle, Seneca, knowledge checkers to quickly test your own knowledge, and you might wish to do this from your own cue cards. The third step is to practice examination questions. So use exam prep books, homework books, supervised study books, additional workbooks to answer exam questions and mark your own work, and you might wish to download your own exam past papers to do this. So the 3 steps are learn the key facts, testing yourself, and practicing examination style questions. Now in this revision session, we'll have 3 different types of questions. The first type of question is the general check question, designed to probe your understanding of the key concepts of the topic. The second part is the checkpoint. These are more challenging questions designed to place your knowledge and understanding of the topics into different contexts and applications. The third type of question is assessment point questions. Now these are past paper examination questions which mimic the types of questions found in public examinations. So let's have a look at thermal physics. So the first question say, describe a liquid in terms of its arrangements of particles, the bonding between them and their motion. Then use the kinetic model of matter to explain the following. If you leave a pan of water on the hob for a long time, it will not all boil away as soon as the temperature reaches 100 degrees Celsius. It takes less time to melt 1 kilogram block of ice at 0 degrees Celsius than to boil away 1 kilogram of water at 100 degrees Celsius, and then when a dog overheats, it pants. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first question, you know that the bonding and links of particles are that for a liquid, bonds are relatively strong. They're stronger than a gas, but weaker than a solid, and the molecules are free to move through the body of the liquid. Now in the second one, 2.1, it's the idea that the energy has to be supplied to convert the liquid into a vapour, which takes time to do this. It takes time to break away those bonds. In the third one, when ice is converted into liquid water, only a few intermolecular bonds will be broken to go from a solid to a liquid, whilst when you go from a liquid to a gas to a vapour, all the molecules are completely separated, all the intermolecular bonds are broken. That requires more energy. And then finally, a dog doesn't actually sweat through his skin like humans do. Instead, they sweat from their tongues. The sweat then evaporates and cools the dog. Now, panting blows air across the tongue, which will increase the rate of evaporation. The next question says, a solid is heated until it melts. The heating continues until a liquid metal boils. Compare the similarities and differences between melting and boiling for a metal. Your answers refer to the energy of the metal, the separation between the atoms of a metal, and the forces between the atoms of a metal. So pause the video now, then unpause the video and you want to go through your answer. Right. What's similar about the solid and the liquid metal? Well, the first thing is, in similarities, energy has to be supplied in both melting and boiling. So it means that both melting and boiling will increase the overall internal energy of the atoms in the metal. Now, in terms of the melting and boiling, it's a change of state. So we know during a change of state, there'll be no change in temperature because there's no change to the kinetic energy store of the substance, only the potential energy store. Now, what are the differences? Now, boiling results in a larger separation between the atoms. So in boiling, the particles are separated so far apart that almost no force will exist between the atoms. Okay, whilst in melting, the atoms are separated sufficiently to slide over each other, but not completely. So we can say that in boiling, the atoms have become pretty much independent of each other and all the intermolecular forces of attraction or intermolecular bonds have been removed. That's not the case when they're melting. Now we also know that boiling occurs at a higher temperature. Temperature is proportional to the kinetic energy store of the object, so therefore the atoms will be moving faster or have a greater kinetic energy during boiling than there would be during melting. And then we also know, as stated previously, more energy is needed to be separating the molecules in boiling compared to when it would be in melting. The next question says, use the first law of thermodynamics to answer the following. A gas is heated by supplying with 250 kilojoules of energy. At the same time, it is compressed so that 500 kilojoules of work is done on the gas. Calculate the change in internal energy of the gas. Then the same gas is heated as before with 250 kilojoules of energy. This time the gas is allowed to expand so that it does 200 kilojoules of work on its surroundings. Calculate the change in the internal energy of the gas. So pause the video now, then unpause the video and you want to go through your answer. Right, what do we know? Well, we know that from the first law of thermodynamics, the change in internal energy is equal to the energy supplied by heating the object plus the energy supplied by doing work on the object as well. Now, you do work on the gas when it is compressed. You do not do work is done by the gas when it's expanding. So we know that there's 250 kilojoules supplied by heating. There's 500 kilojoules supplied when it's compressing the gas. So overall, it's plus 750 kilojoules. So work is going into the gas. In the second one, again, change in internal energy is equal to the energy supplied by the heating plus the energy supplied by doing work on the gas. Now we know here that the gas is expanding, so therefore it's 200 kilojoules out of the gas. So therefore it is minus 200. So it is plus 250 minus 200, so therefore it's 50 kilojoules. The next question says, convert each of the following temperatures from the Celsius scale to the thermodynamic scale, which is the Kelvin scale. So 0 degrees Celsius, 20 degrees Celsius, 120 degrees Celsius, 500 degrees Celsius, minus 23 degrees Celsius, and minus 200 degrees Celsius. Then convert the following temperatures from the thermodynamic or Kelvin scale to the Celsius scale. 0 Kelvin, 20 Kelvin, 100 Kelvin, 300 Kelvin, 373 Kelvin, and 500 Kelvin. And then give one word for each of the following. Add in a scale to a thermometer. All the temperatures from lowest to highest which a thermometer can measure. The extent to which equal rise in temperature give equal changes in a thermometer's output. And then how big a change in output is produced by a given temperature. So pause the video now, then unpause the video and you want to go through your answer. Right, we need to know the difference between the temperature in Kelvin and the temperature in degrees Celsius. So temperature in Kelvin is equal to the temperature in degrees Celsius plus 273.15. So we get 273, 293, 393, 773, 250 and 73 Kelvin. It's the other way around for the next one. So the temperature in degrees Celsius is the temperature in Kelvin minus 273.15. So it's minus 273 degrees Celsius, minus 253 degrees Celsius, minus 173 degrees Celsius, plus 27 degrees Celsius, plus 100 degrees Celsius, and plus 227 degrees Celsius. Adding a scale to a measuring device is called calibration. The values from highest to lowest a measuring device can measure is the range. The extent to which the equal change in temperature given equal change in the output is called linearity, and then how big a change in output is produced by a given change in temperature is the sensitivity of the device. The next question says, a block of paraffin wax was heated gently at a steady rate. The heating was continued after the wax had completely melted. The graph shows how the material's temperature varied during the experiment. For each section of the graph, describe the state of the material. For each section, explain whether the material's internal energy was increasing, decreasing, or remaining the same. Then consider the two sloping sections of the graph. State whether the material's specific heat capacity is greater when it is a solid or when it is a liquid. Justify your answer. So pause the video now, unpause the video and you want to go through your answer. Right, so AB is going to be a solid. BC is when it's melted, so it's a solid and a liquid. And then CD is there when it's fully become a liquid. Now at each part, AB, BC and CD, you are putting energy into the substance by heating it up, so the internal energy is going up in all three sections. Now in the next one, in the two sloping sections, the specific heat capacity is greater when it's a solid, because the specific heat capacity is the energy needed to change the temperature by 1 degree Celsius when you have 1 kilogram. Now the gradient is greater when it's a liquid, so it takes less time to raise the temperature by the same amount when you transfer the same amount of energy, so therefore the less energy is needed. The next question says, calculate the energy which must be supplied to raise the temperature of 5 kilograms of water from 20 degrees to 100 degrees. Then which requires more energy, heating a 2 kilogram block of lead by 30 Kelvin or heating a 4 kilogram block of copper by 5 Kelvin? Then a well insulated 1.2 kilogram block of iron is heated using a 50 watt heater for 4 minutes. The temperature of the block rises from 22 degrees Celsius to 45 degrees Celsius. Find the experimental value for the specific heat capacity of iron. So pause the video now, then unpause the video and you want to go through your answer. Right, we know that to work out the energy supplied when you've got a change in temperature, it's E equals MC, change in temperature. So you can do for each one, and there you get 1.7 megajoules when you pop in all the values. The next one, here again, you work out each one with E equals MC, change in temperature. So for the lead, you'll get 7.56 kilojoules. For the copper, you get 7.60 kilojoules. So the copper block requires more energy. Now, in this instance, it's a bit harder because we haven't got energy, but we have got power and time. So energy is power times time, where time is given in seconds, so therefore our energy will be 12 kilojoules. We can then say C equals E over M change in temperature, so therefore when we work it all through, we get about 435 or 440 joules per kilogram per Kelvin. The next question says, at higher temperatures, the graph shown deviates increasingly from a straight line. Suggest an explanation for this. Then in measurements of the specific capacity of a metal, energy losses to the surroundings are a source of error. Is this a systematic error or a random error? And justify your answer. Then, in an experiment to measure the specific heat capacity of water, a student used an electrical heater to heat up some water. His results are shown below. Calculate a value for the heat capacity of water. Comment on any likely sources of error. So pause the video now, then unpause the video and you want to go through your answer. Right, you've got to remember at higher temperatures that the object will be a greater radiator of energy. So therefore the rate of energy lost to the surroundings is greater, so the temperature rise of the substance will be lower. Now, energy loss to the surroundings is a systematic error because it can be theoretically removed by perfect insulation, which is what we define systematic error to be, an error that can be removed from the experiment by taking away the value of the error. Now in this next one, the first thing we can do is work out the mass of the water by doing the mass of the beaker take away from the mass of the beaker and the water, so we therefore get 0.522 when you work through your answer of grams, which they convert into kilograms afterwards. We can then say power is P equals VI, because we've got current, we've got potential difference, so it's 44.5 watts. In 30 minutes, you can work out the energy supply by doing E equals power times by time. Convert our 13 minutes into seconds, so we get 34.7 kilojoules. We can work out our change in temperature. We can then say C equals E over M times by change in temperature. We then work it all through and we get 5,700 joules per kilogram per Kelvin. Now, the biggest source of error, as mentioned before, will be the energy loss due to the surroundings. Now, this could also include the energy being given to the beaker itself, so therefore we can reduce that by insulating the entire substance. The next question says, a student measured the temperature of some oil in a beaker. The temperature of the oil is 20 degrees Celsius. Give this temperature in Kelvin. Then the student heats 600 grams of oil using an immersion heater. The temperature of the oil increases from 300 Kelvin to 350 Kelvin, so that the minimum amount of energy supplied to the oil is approximately 63,000 joules. The specific heat capacity of the oil is 2,090 joules per kilogram per Kelvin. So pause the video now, then unpause the video when you want to go through your answer. Right, so we can convert from degrees Celsius into Kelvin by adding 273.15, that's 293.15 Kelvin. Here we know E equals MC triangle T. We convert our grams into kilograms. We then work out our change in temperature to be 50. We pop in all the values and we get 62,700 joules. The next question says, describe the changes to the kinetic energy, the potential energy, and the total internal energy of the molecules of a block of ice as it melts at 0 degrees Celsius and as the temperature of the water rises from 0 degrees Celsius to room temperature. Then explain in terms of kinetic energy why the temperature of a stone increases when it falls from a cliff and lands on a beach. Explain why the barrel of a bicycle pump gets very hot as it's used to pump up a bicycle tyre. And then the zeroth law of thermodynamics states that if the temperature of a body A is equal to the temperature of body B, and the temperature of body B is the same as body C, then the temperature of body C equals that of the temperature of body A. Explain in terms of energy flow why the concept of temperature will be meaningless if this law was not obeyed. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, because we're changing state, the kinetic energy remains constant. The potential energy will increase because we are changing state by heating it up, so therefore the overall internal energy increases. In this next one, the kinetic energy will increase as the temperature increases. The potential energy remains constant, so therefore the overall internal energy will increase. Now in this next one, just before the stone hits the ground, it has kinetic energy. So all the molecules moving together in the same direction. When it hits the ground, the unidirectional movement of the molecules is converted into the movement of individual molecules or random direction. So therefore the kinetic energy from movement in random directions is the internal energy, and therefore the temperature will rise. In the next one, the air is being compressed, so work is being done on it. So from the first law of thermodynamics, the change in the internal energy of a body is equal to the energy supplied by heating plus the energy supplied by doing work. So therefore there's no energy supplied by heating, but work is being done by compressing that gas, by compressing the air. Now in this last one, if two bodies are the same temperature, no energy flow will happen from one body to another. So therefore if no energy flows from A to B and none flows from B to C, but if energy did flow from C to B, it would mean that A and B were the same temperature, and A and C are the same temperature, but C will be hotter than B, which is clearly not correct, which is a fundamental law in thermodynamics. The next question says, the specific latent heat of vaporization of water is 2.26 megajoules per kilogram. Calculate the energy needed to change 2 grams of water into steam at 100 degrees Celsius. The specific latent heat of fusion of water is 330 kilojoules per kilogram. Calculate the energy needed to change 2 grams of ice into water at 0 degrees Celsius. Suggest why the answer is much smaller than the amount calculated in 1.1. Then a sample of alcohol is heated with a 40 watt heater until it boils. As it boils, the mass of liquid decreases at a rate of 2.25 grams per minute. Assuming that 80% of the energy supplied by the heater is transferred to the alcohol, estimate the specific latent heat of vaporization of the alcohol, given your answer in kilojoules per kilogram. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one we know E equals ml, that's the equation for latent heat, so therefore we can pop in the values. Remember to convert grams into kilograms, convert the megajoules per kilogram into joules per kilogram, so therefore it's 4,520 joules. In this next question, E equals ml again, convert our grams into kilograms and our kilojoules per kilogram into joules per kilogram. So when you multiply them together, we get 660 joules. Now when a solid melts, only about one bond per atom or molecule is broken in the melting process. But in boiling, all of the bonds are broken, so it needs more energy to do this. Now in this next question, we know that the rate of loss of mass is 2.25 grams per minute, so we can work that into seconds and say it's therefore 3.75 times 10 to the minus 5 kilograms per second. Now the energy supplied to the alcohol is 80% of the energy supplied by the heater, so 40 times by 0.8 is 32 watts, so therefore the latent heat, L, is going to be equal to E over M, or the rate of energy supplied, divided by the rate of mass loss, so therefore it's the power over the rate of mass loss, so we can pop those values in, and we get 850 kilojoules per kilogram. The next question says, a cylinder contains 0.80 decimeters cubed of nitrogen gas at a pressure of 1.2 atmospheres. A piston slowly compresses the gas to a pressure of 6 atmospheres. The temperature remains constant. Calculate the final volume of the gas. Then a balloon contains 0.04 meters cubed of air at a pressure of 120 kilopascals. Calculate the pressure required to reduce its volume to 0.025 meters cubed at a constant temperature. So pause the video now, then unpause the video and you want to go through your answer. Right, here we've got to remember that Boyle's law, that P1V1 equals P2V2. You don't need to change units because it's a ratio, so you pop in the values, so you get 0.16 decimeters cubed. Do the same for the next one. We can work it all through. Here we can then change it into pascals just to make it easier and work out our value. So we work it through and we get 1.9 times 10 to the 5 pascals. The next question says, a sealed container contains 60 moles of gas at a temperature of 250 Kelvin and a pressure of 60,000 pascals. Calculate the volume of the container. State the effect on the pressure of a fixed mass of gas at constant temperature if the volume of the gas is doubled or reduced to a third of its original value. Then a fixed mass and volume of gas initially at a temperature of 20 degrees Celsius and a pressure of 300 kilopascals is heated to 100 degrees Celsius. Calculate the change in pressure. So pause the video now, then unpause the video and you want to go through your answer. Right, in this first one, we've got moles, we've got temperature in Kelvin, we've got pressure. So we can say PV equals nRT, the ideal gas equation. So V equals nRT over P. R is the molar gas constant given to your new equation sheet. Pop in all the values, 2.1 meters cubed. We can say here, if you remember for Boyle's law, that P and V are directly inversely proportional to each other. So therefore, if the volume is doubled, the pressure will half. And if the volume is reduced to a third, well then P would increase by 3 or would triple. Now in this next one, we know from the second law, from Charles's gas law, that P over T is a constant. So we can work out what that constant is from the initial values given. So it's 300,000 over 293. We converted our temperature into Kelvin and our pressure into pascals, so we get 1020. So therefore afterwards we can say pressure is that constant times by the new temperature, again in Kelvin, so therefore we work out the new pressure is 401,000 pascals and it asks for the change in pressure, so find the difference between that and the starting pressure of 300,000, so it's 101,000 pascals. The next question says, Figure 4 shows an example of a Carnot cycle engine. The cylinder contains a fixed mass of gas. The piston moves in the direction as shown. Explain what happens to the internal energy of the gas, refer to the motion of the gas molecules and the gas temperature. A cylinder contains some gas at a temperature of 400 Kelvin. The pressure of the gas in the cylinder is 201,400 pascals. The cylinder and the gas inside the cylinder cool to 293 Kelvin with no change in volume. Calculate the pressure of the gas when its temperature is 293 Kelvin. So pause the video now, then unpause the video and you want to go through your answer. Right, we know that the internal energy of the gas will increase. Why is that? Well, the gas is being compressed, so therefore work must be being done onto the gas. So therefore energy is being placed into the gas. This will cause the temperature to increase because in theory there's no potential energy in the gas, because therefore the molecules will have a high kinetic energy. In this next one, again we use P1V1 equals P2V2. We work it all through, remember popping all the values in and we get 148,000 pascals. The next question says, consider a smoke particle of mass m and speed v. It is constantly buffeted by air molecules. The mass of a single air molecule is m and its speed is v. It is reasonable to assume that on average the smoke particle will have a kinetic energy approximately equal to the kinetic energy of a single air molecule. Show that big M is much greater than small m, and it follows that the air molecules must be moving much faster than the smoke grain. Then if equal numbers of air molecules hit a smoke particle from all directions, the smoke particle does not move. State 3 ways in which the random movement of molecules of air causes the smoke particle to move. Describe and explain what you would see through a microscope observing Brownian motion when the temperature increases. Then an oxygen molecule is moving around inside a spherical container of diameter 0.10 meters. The molecule speed is 400 meters per second. Estimate the number of times each second the molecule collides with the container's walls. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, the time taken to cross the diameter of the container once is distance over time, which you can work through with the values roughly to be about 2.5 times 10 to the minus 4 seconds. So if you assume a molecule speed is constant and therefore each collision is including like that, okay, well therefore you can say the number of collisions is 1 over time, so it's 1 over 2.5 times 10 to the minus 4, so it's about 400 collisions every second. Now, it's different because the different number of molecules hit one side than the other. The number of molecules striking on any area per second will vary. The speed of the molecules hitting will vary, and the angle that the molecules hit the smoke detector will also vary. The next one, you'll see with Brownian motion, the smoke particles will move faster and more erratically because at a higher temperature, the molecules of air will be moving faster because temperature links to the kinetic energy of the molecule. So therefore, the impact will cause a greater change in the momentum of the smoke particle. Okay, and then finally, okay, as we said before, the answer is going to be 400 times per second. Now the next question says, state and explain in terms of the kinetic model what happens to the pressure inside a tyre when more molecules at the same temperature are pumped into the tyre. Then explain using the kinetic model why a can containing air may explode if the temperature rises. So pause the video now, then unpause the video when you want to go through your answer. Right, remember that pressure is caused by the change in momentum that the particles have on the side of a container. So the pressure increases because more particles are hitting a unit area of the tyre every single second. The frequency of collisions has gone up. So the molecules have the same speed because they've got the same temperature, and temperature links to kinetic energy. So each collision will cause the same impulse or change in momentum. Now since more molecules hit per second, the rate of change in momentum, which is the force, will increase, which increases the pressure. Now in the next one, at higher temperatures, the molecules have higher internal energy and therefore move faster because the only internal energy they have is kinetic energy. So the number of collisions per second will increase, and the change in momentum of each collision will also increase because they're hitting harder. So for both these reasons, the rate of change of momentum of the molecules increases. Now the force on the wall is equal and opposite to the rate of change of the momentum of the molecules, so as the force increases, the pressure inside the can will also increase, which may cause it to explode. In the next question it says, check that the units on the left hand side of the equation, P equals a third, nm over v times by c squared, are the same as those on the right hand side. Then the quantity nm is the total mass of the molecules of the gas. So the mass of the gas. At room temperature, the density of air is about 1.29 kilograms per meters cubed at a pressure of 10 to the 5 pascals. Use these figures to deduce the value of c squared for air molecules at room temperature, and then find a typical value for the speed of a molecule in air by calculating the root of c squared. How does this compare with the speed of sound in air? So pause the video now, then unpause the video when you want to go through your answer. Right, let's look at some dimensional analysis. So the units of pressure is P equals F over A, so therefore it's MA over A, which we can therefore say is kg ms to the minus 2 over m squared. So therefore the overall units of pressure are kg m to the minus 1 s to the minus 2. Whilst on the right hand side, we can say it's nm times by c squared over v, so therefore it's going to be kilograms because n is just a number, so it'll have no values. So it'll be kg, there'll be ms to the minus 1 squared because it's going to be speed squared divided by the volume, which is meters cubed, which goes to be kg m to the minus 1 s to the minus 2, which is the same units on each side. In this next one, we can rearrange the equation to say P equals Nm times by C squared over 3V. So therefore C squared is equal to 3PV over Nm. Pop in all the values, we can work it through. Now remember, density is mass over volume, so therefore you can link it to dividing by the density because it's going to be m over v. So therefore it's 3 times 10 to the 5 times by 1 over 1.29, 2.3 times 10 to the 5 meters squared seconds to the minus 2. Then we can work out our answer by square rooting this value to be 480 meters per second, which is about 50% greater than the speed of sound and air, 330 meters per second. The next question says the Boltzmann constant K is equal to R over Na. From the values of R and Na, show that K has a value of 1.38 times 10 to the minus 23 joules per Kelvin. Then write down an equation linking the Boltzmann constant, the thermodynamic temperature, and the average kinetic energy of a molecule. Calculate the mean kinetic energy of atoms in an ideal gas at 27 degrees Celsius. The atoms in a gas have a mean kinetic energy equal to 5 times 10 to the minus 21 joules. Calculate the temperature of the gas in Kelvin and then in degrees Celsius, and then show that if the mean speed of the molecules in an ideal gas is doubled, well then the thermodynamic or Kelvin absolute temperature in Kelvin of a gas is increased by a factor of 4. So pause the video now, then unpause the video when you want to go through your answer. Right, we can work out the Boltzmann constant because K is equal to R over Na. You're given R, you're given Na on the equation sheet, so you get 1.38 times 10 to the minus 23 joules per Kelvin. The next one we know from the equation sheet that the kinetic energy of one molecule is 3 over 2 kT, where T is in Kelvin. So therefore we work it through by saying, well, 3 over 2 kT or 3 over 2 RT over Na. Pop in all the values, convert the temperature into Kelvin. So we get 300, and then we work it through to be 6.2 times 10 to the minus 21 joules. In this next one again, we can say, well, kinetic energy is equal to 3 over 2 kT or is equal to a half mc squared, so half mv squared. Pop in all the values, remember to make T the subject, which is 242 Kelvin or minus 31 degrees Celsius. Then we can see that temperature from the previous equation is going to be proportional to the average speed squared. So therefore, if the speed doubles, well then the temperature will increase by a factor of 2 squared, which is 4. The next question says, a fixed mass of gas expands to twice its original volume at a constant temperature. How do the following change? The pressure of the gas and the mean kinetic energy of the gas molecules. Air consists of oxygen, molar mass 32 grams per mole, and nitrogen, molar mass 28 grams per mole. Calculate the mean kinetic energy of these molecules in air at 20 degrees, then estimate the typical speed for each type of molecule, and then show that the change in internal energy of 1 mole of an ideal gas per unit change in temperature is always constant, and what is this constant going to be? So pause the video now, then unpause the video when you want to go through your answer. Right, we can see that, like we said before, PV equals to a constant. So therefore, if we can work it through to say that if it's now twice its original volume, well, therefore the pressure will halve. Now the kinetic energy will remain the same because E equals 3 over 2 kT. K and T are constant, so therefore the kinetic energy will be constant. We can work out the kinetic energy for each one by doing 3 over 2 kT, or we could be doing a half mv squared. Now m is the mass of one molecule, so you can work that through by doing, well, the molar mass is divided by Avogadro's constant is going to therefore give you the mass of one molecule, because the molar mass is the mass of one mole. The Avogadro's constant is the number of molecules in 1 mole, so therefore you can work it through that way. So when you work it all through, make V the subject to work out the average speed of the molecule. Oxygen comes out to be 480 meters per second, and nitrogen comes out to be 510 meters per second. Now, like we said before, we can say that the internal energy is going to be the kinetic energy store, because in a gas there's no potential energy in that gas, so it's only kinetic energy being the internal energy store. So therefore it's the kinetic energy of one molecule, 3 over 2 kT, times by the number of molecules in that gas, which is 1 mole, so therefore it is Avogadro's constant. We know that, therefore we can say that Na, okay, then in that point divided by K at that point, so times by K will equal R, so therefore it's 3 over 2 RT, so therefore the change per Kelvin is 3 over 2R. The next question says, describe what happens to the absolute temperature of a gas if the RMS speed of the particles in the gas firstly increases, then doubles, then increases by a factor of 5. Then the gas canister has a volume of 0.50 meters cubed. The pressure inside the canister is 450 kilopascals and the temperature is 18 degrees Celsius. Calculate the number of particles of the gas and the number of moles inside the canister. Then explain why doubling the temperature of a real gas does not double the internal energy. So pause the video now, then unpause the video when you want to go through your answer. Right, well, firstly, we know that temperature links into speed because they're proportional to each other. Okay, so therefore, as the temperature increases, well, therefore the speed will also increase. Okay, next one, we know that temperature is actually proportional. Okay, so it links to the speed squared. So if the speed doubles, well then the kinetic energy will quadruple as the temperature will also quadruple. And then once again, if the speed increases by a factor of 5, the kinetic energy and the temperature will increase by a factor of 25 because it's proportional to 5 squared. Now in the next question, we can work out the value here by saying PV equals big N kT. That's another ideal gas equation. So N equals PV over kT. Remember, P is in pascals, not kilopascals. So you can pop in all those values, convert 18 degrees Celsius into Kelvin. So you get 5.6 times 10 to the 25 particles. Divide that then by Avogadro's constant, the number of particles in 1 mole, to work out the number of moles. So we get 93.1 moles. Now in the last question, double the temperature of a gas in the real world doesn't actually double the internal energy. It will double the kinetic energy of the atoms in the gas, but the atoms and molecules in a real gas will also have potential energies, which we don't assume in an ideal gas. So in a real gas, the internal energy is equal to the sum of the kinetic and the potential energies of the atoms within the gas. So doubling the kinetic energy won't equal the doubling the internal energy because there's potential energy there as well. The next question says, an oxygen molecule has a mass of 5.3 times 10 to the minus 26 kilograms. Calculate the RMS speed of an oxygen molecule at room temperature. Then compare the kinetic energy and RMS speed of room temperature of a helium atom of mass 6.6 times 10 to the minus 27 kilograms with the answer to the previous question. So pause the video now, then unpause the video when you want to go through your answer. Right, we can say, well, a half mv squared or half mc squared is equal to 3 over 2 kT. Rearrange it, make the speed the subject, pop in all the values, change the temperature into Kelvin, so therefore we get 480 meters per second. Now we should know that kinetic energy is 3 over 2 kT, so because they're at the same temperature, room temperature, they'll have the same kinetic energy, but the speed of the helium atom will be greater because the oxygen molecule has 8 times as much mass as the helium one does. So therefore, to have the same kinetic energy, the helium must be travelling at 2.8 times, or square root 8, because a half mv squared, faster, so they link in like that. The next question says, wax is heated until the temperature is melted above the melting point of the wax. The hot wax is poured into a bowl and allowed to cool. The graph shows how the temperature of the wax varies with time as it cools. Describe how the internal energy of the wax changes as the wax cools. You should refer to the energy of the wax molecules as the liquid cools and becomes a solid, and the solid wax cools. Times x and y have been included to help refer to the graph. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, the internal energy of the wax decreases during cooling because energy is leaving the substance. So the internal energy is the sum of the potential and the kinetic energy of the molecules. As the temperature decreases, then the kinetic energy store of the molecules will decrease. So between times x and y, as it's solidifying, the potential energy store decreases because it's changing state. Between times x and y, the temperature is constant because there's no change in the kinetic energy store. At time y, the wax is finished solidifying and the temperature then starts to drop. The next question says, a 500 watt kettle contains 300 grams of water at 20 degrees Celsius. Calculate the minimum time it would take to raise the temperature of the water to boiling point. Then the kettle is allowed to boil for 2 minutes. Calculate the mass of the water that remains in the kettle, stating any assumptions that you make. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we can see E equals MC triangle T, or change in temperature, because there's a change in temperature here. Convert our grams into kilograms, and we work it through to be equal to 100,320 joules. Time is energy over power. We know it takes 500 seconds, because we work in 500 watts there. So we get our answer out to be 201 seconds. Now we're assuming no energy goes into heating the element, or the kettle, or is being lost to the surroundings. Now in this next one, again, we say E equals power times times by time. So it's 500 times by 120. Minutes go into seconds, so we get 60,000 joules. The mass of water boiled away, because it's a change in energy, a change in state, is going to be E over the specific latent heat. So it's 60,000 over 2.26 times 10 to the 6, which is 0.027 kilograms. So therefore that's 27 grams. So therefore the mass left over is going to be 300 grams, the starting mass, which is told you the previous part of the question, minus 27. So it's about 270 grams. Now assuming here that no energy is lost to the surroundings and all the vapor will escape the kettle. The next question says, explain what is meant by the specific heat capacity of a substance. Now the figure shows the apparatus used to measure the specific heat capacity of a copper block of mass 850 grams. The block is initially at 12 degrees Celsius. The heater is switched on and the time taken for the temperature to rise to 30 degrees is recorded. The block is cooled to the original temperature and the potential difference across the heater is increased and the experiment is repeated. The results are shown below. Explain why a thermocouple thermometer is suitable for this experiment. Explain why the experiment is repeated using a different power input and calculate the specific heat capacity of the copper. So pause the video now, then unpause the video when you want to go through your answer. Right, so the first one's a definition. So it is the energy required to raise the temperature of 1 kilogram or a unit mass of a substance by 1 degree Celsius. Now a thermocouple thermometer is used because it has a very small heat capacity and it can quickly act and will quickly record the temperature. The next one, we will use different power inputs to allow for energy losses to the surroundings. So to work out the heat capacity, you'll do the input of the energy, which is 40 times by 190, so 7,600 joules. The experiment one is the energy input is MC triangle T plus the energy losses. So you can work that through to be 7,600 equals 15.3 C plus Q1. Same for experiment 2, and you get 6,840 equals 15.3 plus Q2. You can then subtract the equations 1 and 2 to get 7,600 minus 6,840 equals Q1 minus Q2. We can then sub that into the previous equations, and therefore we can work out Q1 to be 1,900 joules. So therefore when you pop it into the equation for 1, we will say 7,600 equals 15.3 C plus 1,900, we get 372 joules per kilogram per degree Celsius. The next question says, an electric shower runs at 230 volts and 46 amps. In the summer, it increases the water temperature from 22 degrees Celsius to 39 degrees Celsius. Calculate the thermal energy used to increase the temperature of 1 kilogram of the water. Now, the heat capacity of the water is 4,200 joules per kilogram per Kelvin. Calculate the time it will take the heater to deliver this amount of thermal energy. In winter, the inlet water temperature drops to 5 degrees Celsius, but the final temperature remains at 39 degrees Celsius. State and explain the change to the water flow rate for this shower in winter compared to summer. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, E equals MC triangle T, or change in temperature. So it's 4,200 times by 1 times by 17, 71.4 kilojoules. Now we can say T equals this energy, okay, divided by IV, or the power. So therefore it's 71.4 times 10 to the 3 over the power, which is 230 times by 46, is 6.75 seconds. And we can say in this next one, the change in temperature is doubled, so therefore the flow rate, or the change in mass per time, is going to have to half to keep that constant value for C, because we can see that C is going to equal to be delta E over MC triangle T, or delta phi, so therefore it's going to have to half for when the change in temperature is doubled. The next question says, cocoa powder, milk and hot water are mixed together to produce a hot chocolate. The mass of the drink is 275 grams and its initial temperature is 71.5 degrees Celsius. The ice at 0.0 degrees Celsius is added to the drink to reduce its temperature. Research indicates that the maximum serving temperature of any hot drink should be 58.0 degrees Celsius. Deduce whether 4 grams of ice would be enough to bring the temperature below 58.0 degrees Celsius. So pause the video now, then unpause the video when you want to go through your answer. Right, in this question we can say that the energy transfer from the hot liquid is the energy transferred to the ice plus the energy transferred to the cold water. So we can say that E is going to equal MC, change in temperature, so 0.275 times by 3,750 times by 71.5 minus 58, which will equal those two other energies, so M times by L plus by M times by C times by change in temperature. So we can work that through, and we've got M coming out as a constant term. So as you can see here, M is going to equal 1.39 times 10 to the 4 over 5.77 times 10 to the 5, which equals about 24 grams. So adding 4 grams wouldn't bring the temperature below the ideal serving temperature. You would in fact need 24 grams for this to work. The next question says, lead shot contains a small lead spheres. Originally, lead shot was made by dripping molten lead through copper sieve from the top of a shot tower. The lead cooled as it fell before landing in the water and producing solid lead spheres. Figure 1 shows a shot tower and Figure 2 shows the process of a lead shot in the shot tower. Now, to avoid producing steam, the temperature of the lead was below 100 degrees Celsius as it reached the cold water. As the lead sphere falls through the distance of 41.5 meters, so it takes 3 seconds for the lead sphere to fall this distance, assuming that resistive forces are negligible. The lead sphere has a radius of 1.2 millimeters. As it falls, it cools from 615 to 370 Kelvin. The molten lead solidifies at 601 Kelvin. Calculate the mean rate at which the energy is transferred from the lead sphere to the surroundings. You should assume that the sphere heat capacity of liquid lead and the solid lead are the same. So pause the video now, then unpause the video when you want to go through your answer. Right, we can just use suvat in this question because it's going to be constant acceleration. So S equals ut plus a half at squared. Remember, A is minus 9.81 and S is minus 41.5. So therefore T will equal 2.91 seconds. In this next one, we work out what the volume is going to be by doing 4 over 3 pi r cubed. So we get our volume out. We can then say the mass is the density times by the volume. So we get our mass to be 8.18 times 10 to the minus 5 kilograms. We can then say, well, what's the energy change going to be when it changes temperature? We do E equals MC change in temperature. Pop in all those values and you get 2.61 joules. We can then look at E equals ml as it changes state, as it solidifies, by doing mass times by the latent heat capacity, which is 2.02 joules. So add the two together, that's the energy change, divided by the time will give you the power, so you get 1.60 watts. The next question says, a student learns that the energy required to heat water for a bath can be 10 times the energy required to heat water for a shower. The student uses the shower for 9 minutes and the water comes out the shower at 38 degrees at a flow rate of 1.8 times 10 to the minus 5 meters cubed per second. The student usually fills the bath with 160 kilograms of water at 32 degrees Celsius. Deduce whether the bath uses 10 times more energy than the shower. So pause the video now, then unpause the video when you want to go through your answer. Right, so what we can do is work out the energy change for each one. So in the let's have a look at the bath first. So E equals MC triangle T, or change in temperature. So you can pop in all the values and then we pop out, we get 1.14 times 10 to the 7 joules. Now look for the shower. What's the mass going to be? Well, in 1 second the mass is going to be the flow rate for that 1 second. So it's going to be 1 times 10 to the 3 kilograms per meters cubed times by 1.8 times 10 to the minus 5, because we're saying mass is density times by volume. So therefore it's going to be 0.018 kilograms. So therefore we can then work out what it's going to be for 60 seconds. So say they're in the shower for 9 minutes, so do 60 seconds times by 9, so it's 0.018 times by 9 times by 60 is 9.72 kilograms. So therefore E equals MC change in temperature for this one, and we'll say it's 38 to 15, so there's your difference there. So it's 9.34 times 10 to the 5. Find the ratio of the two, and it's 12.2 times, so actually it is more than 10 times. The next question says, ice cubes can be made in an ice cube tray. One type of ice cube is shown. Each compartment in the ice cube tray has dimensions of 2.5 centimeters by 2.5 centimeters by 3.5 centimeters. Show that the mass of the water needed to fill one compartment is about 0.02 kilograms. Then all 6 compartments in the ice cube tray are filled with the water to a depth of 3.5 centimeters. The ice cube tray is placed in a freezer. The initial temperature of the water is 22.5 degrees Celsius. It takes 12 minutes for all the water to become ice at 0 degrees Celsius. The manufacturer of the freezer states that the freezer can transfer energy at a rate of 110 watts. Evaluate whether energy is transferred from the water in the tray at a rate of 110 watts. So pause the video now, then unpause the video when you want to go through your answer. Right, so we know density is mass over volume, so therefore volume is going to work out to be the mass, okay, divided by, so you can work out what the volume is going to be by doing 2.5 times 10 to the minus 2 times by 2.5 times 10 to the minus 2 times by 3.5 times 10 to the minus 2, turning centimeters into meters, so we get 2.19 times 10 to the minus 5. We can therefore say that the mass is going to be working it through to be the density times by the volume. So we've got the density, we've got the volume, multiply them together, we get 0.0219 kilograms. In this next one, we can say that the change in energy is MC change in temperature. Pop it all through. Now again, remember, it is going to be 22.5 because it starts at 0 and goes to 20, or starts at 22.5 and goes to 0. Pop in all the values, remember there's 6 of them when you're working out the mass, so it's 1.24 times 10 to the 4 joules. We can therefore say E equals ml because there's also freezing and change in state. Remember the mass is 6 of them. Then multiply by the latent heat of fusion, and we get 4.41 times 10 to the 4. Add the two together to get the total energy change, divided by the time, which is going to be in seconds, not minutes. So we work it through to be 78.5 watts. So therefore, it is not at a rate of 110 watts. The next question says, a cylinder holds 140 decimeters cubed of nitrogen at room temperature and pressure. Moving slowly so that there is no change in temperature, a piston is pushed to reduce the volume of nitrogen to 42 decimeters cubed. Calculate the pressure of the nitrogen after compression. Explain the effect on the temperature and pressure of the nitrogen if the piston was pushed in very quickly. Then the atmospheric pressure is 100 kilopascals, equivalent to the pressure exerted by a column of water 10 meters high. A ball of oxygen of volume 0.42 centimeters cubed is released by a water plant at a depth of 25 meters. Calculate the volume of the bubble when it reaches the surface. State any assumptions that you make. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one again, we're using Boyle's law. So P1V1 equals P2V2. So P2 is going to be equal to 3.4 times 10 to the 5 pascals. Remember, you don't have to change the units because it's just a ratio. Now we know that PV equals a constant, so therefore, what else do we know about that? That in the other way around, we can link in pressure and temperature as well. So when the temperature of the gas increases, that will cause the pressure to be higher than the previous question. Again, we can also now use Boyle's law again to work out what V2 is going to be. Again, you don't need to change units as long as it's in the same unit. So therefore, the answer is going to be 1.5 centimeters cubed. Again, this assumes that the temperature at a 25 meter depth is equal to the temperature of the surface of the water for it to work through, because we can only work if it's a constant temperature. So we get 1.5 centimeters cubed. The next question says, this question is about an investigation into the relationship between pressure and volume of a gas. This is often referred to as Boyle's law. A student sets up the apparatus as shown in the picture. Identify a variables needs to be controlled in the investigation. Then before setting up the apparatus, the student took measurements of the vernier calipers of the internal diameter of the tube containing the gas. The student created a dot plot of the cross-sectional area as shown. Taking into consideration any outliers, calculate the value for the mean and percentage uncertainty of the cross-sectional area of the tube, given your answers to the appropriate number of significant figures. So pause the video now, then unpause the video when you want to go through your answer. Right, you've got to know that for Boyle's law, it only works if the temperature is constant, so that's the control. Now, if you look at the information given in the previous question, you can identify there's an outlier or anomalous result, it's 79. So therefore, you can calculate the mean correctly. So the range, work out the uncertainty by doing half the range. So therefore, you can work out the percentage uncertainty by doing the uncertainty value, which you've worked it through from working out absolute uncertainty is range divided by 2. You then divide it by the mean value, you times it by 100, and you should be getting out about 4 or 5%. The next question says, the pressure of a gas is changed and the values for absolute pressure and height of a column of gas are recorded. The data is shown in the table below. The student plots a graph to show how the relationship between the height of the column of the gas and 1 over pressure are shown. Suggest with reasons how the presentation of the graph could be improved and identify any anomalous points. The student also calculates the gradient to be 25 times 10 to the minus 6 kilonewtons per meter. Explain the physical significance of the gradient, state the assumptions and estimate n, the number of molecules of the gas that will be present at a temperature of 298 Kelvin. So pause the video now, then unpause the video when you want to go through your answer. Right, so firstly, how could you work this all through? So the presentation, looking at it, the x-axis scale could go with a more appropriate scale. The y-axis should be made larger so that more plotted points cover over half the grid. You should have the plotted points growing precisely with crosses. The line of best fit's probably too steep. The third data point is anomalous. You have to have error bars onto the plots, and you should have units on your y-axis. If you think of the equation as PV equals nRT, well therefore 1 over P equals V over nRT. We know volume is area times by height, and the gradient therefore of the line is area over nRT. So therefore we can rearrange it to work out that the number of moles is going to be equal to A over RT times by the gradient. That allows you to work it through to be 1.4 times 10 to the minus 3 moles. Our assumptions are the gas is ideal, it is monoatomic, it is no interactions between each other, the particles have a negligible volume, they have perfectly elastic collisions, and the time taken for any collisions is considered to be negligible or extremely small. The next question says, the escape velocity is the minimum speed needed for an object to escape the gravitational field of a planet. An object travelling at the escape velocity has a kinetic energy equal to the magnitude of its gravitational potential energy at the surface of the planet. Show that the escape velocity v for a planet of mass m in radius r is given by the expression v equals the square root of 2gm over r. Then show that the escape velocity for a mass of the Earth's surface is about 1.1 times 10 to the 4 meters per second. Then when the Earth formed, a large proportion of the gas in the Earth's atmosphere was hydrogen. Explain why the hydrogen gas is no longer a large proportion of the Earth's atmosphere. At 20 degrees, the root mean square speed is 1900 meters per second for hydrogen. So pause the video now, then unpause the video when you want to go through your answer. Right, so what we can say is we can say that the energy is equal to m times by the change in potential, which is equal to gmm over r. We can therefore say a half mv squared, which is the change in energy, is equal to gmm over r. So therefore v is equal to 2gm over r. So therefore v equals the square root of 2gm over r. You can pop in all your values given in the previous question. You work it all through. G is given on the equation sheet, and we get 1.12 times 10 to the 4 meters per second. Now, you've got to understand that even though you've got a root mean square speed, that's actually a range of molecular speeds. Some molecules will travel much faster than 1900 meters per second, while some will be traveling a lot slower. It's just an average speed. So there'll be some molecules that have a greater speed than the escape velocity, which is 1.12 times 10 to the 4 meters per second, and therefore there'll be some molecules with a high enough kinetic energy to escape, which is why lots of that hydrogen gas has left the Earth's atmosphere. The next question says, a cylinder contains 40 decimeters cubed of carbon dioxide at a pressure of 4.8 times 10 to 5 pascals at room temperature. Calculate the number of moles of carbon dioxide, the mass of carbon dioxide, then calculate the volume of 1 mole of ideal gas at a pressure of 1.01 times 10 to 5 pascals at a temperature of 0 degrees Celsius. Then a vessel of volume 200 decimeters cubed contains 3 times 10 to 26 molecules of a gas at a room temperature of 127 degrees Celsius. Calculate the pressure exerted by the gas on the vessel walls. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one we can say N equals PV over RT, the ideal gas equation. Remember to change to work out what the room temperature is. It's 20 degrees Celsius or 293 Kelvin. Pop it all through, 7.9 moles. We can work out, when you work it all through here, we can say, well, we can work it by saying N equals PV equals nRT, and we can work out what that value is going to be, 7.9 moles. We can then work that through by saying it's 350 grams by using our relative molecular mass, because mass equals moles over mR. Now the next question we can say, well, V equals nRT over P, pop in all the values, work it through, 22.4 decimeters cubed. Here again, P equals big N KT over V, pop in all the values because now you've got N, which is the number of molecules in the question, pop it all through, and then you get your answer. Remember, temperature is going to be in Kelvin, not degrees Celsius, 8.31 times 10 to the 6 pascals. The next question says, explain what is meant by an ideal gas. Then a cylinder contains 500 grams of helium at a pressure of 5 times 10 to 5 pascals at a temperature of 27 degrees Celsius. You may assume that helium acts as an ideal gas. So the number of molecules of calculate the number of moles of helium the cylinder holds, the number of atoms of helium the cylinder holds, calculate the volume of the cylinder. When the tap of the cylinder is open for a short time, a small amount of helium escapes into the atmosphere. As it does so, the temperature of helium drops significantly. Explain why the temperature drops, then describe what happens to the average speed of the atoms of the escaped helium. So pause the video now, then unpause the video when you want to go through your answer. Right, definition of an ideal gas, you've got to learn it. It's a gas that obeys the ideal gas laws at all temperatures and all pressures. In this next one, it's 125 moles because we've got the, we know the mass of the helium is 500 grams and we know what the MR of helium is, it's 2. So moles is mass over MR, 500 divided by 2 is therefore going to be 125 moles. Multiply that by Avogadro's constant, the number of molecules in 1 mole to get the number of molecules, 7.53 times 10 to the 25 molecules. We can then work out the volume because V equals nRT over P, pop in all the values, and we get 0.62 times 10 meters cubed. Remember, temperature is in Kelvin, not in degrees Celsius. The temperature drops because what happens is the helium does work on the atmosphere because it's going to expand into the atmosphere, so energy is taken from the helium as it expands out, so therefore its temperature will drop. Remember that work is done when it compresses and work is done out of it when it expands, and then as the temperature goes down, well therefore the kinetic energy goes down, so the average speed of the particles will drop. The next question says, a hot air balloon is basket and passengers have a total mass of 540 kilograms. The inflated balloon holds 3,000 meters cubed of air. Calculate the minimum force needed to lift the balloon off the ground. Atmospheric pressure is 1.03 times 10 to the 5 pascals and the density of air at this pressure is 1.23 kilograms per meter cubed. Calculate the mass of 3,000 meters cubed of air. Calculate the number of moles of air in the balloon. You may consider the air of this pressure to act as an ideal gas with a relative molecular mass of 29. As the air is heated, it expands. Some of it is expelled through a vent at the top of the balloon. Calculate the maximum mass of the air that can remain in the balloon to give sufficient upthrust for the balloon to just leave the ground. And then calculate the minimum temperature that the air inside the balloon must be heated for the balloon to just lift off the ground. So pause the video now, then unpause the video when you want to go through your answers. Right, in this next one, what's the minimum force required? Well, it's going to be equal to the weight of the object. So 540 times by 9.81 is 4,410 newtons. In this next one, we can work out what the mass is going to be by doing mass is therefore going to be equal to density times by volume. We've got the pressure, and we can work it all through. We've got the density there. We've got the volume. We can work it out. So therefore, it's going to be 3,690 kilograms. Now, the number of moles is therefore going to be mass over the MR. So you can work it through that way. That gives you the number of moles to work it through. And then the next bit here is to achieve the lift, a minimum of 450 kilograms of air must leave the balloon. So therefore, the maximum mass of the air remaining to be 3,690, which we've worked out as the mass of the air, minus 450, which is 3,240 kilograms. And then the remaining air is therefore going to be divided therefore by 29 times 10 to the minus 3 to work out our number of moles. PV equals nRT, so therefore T is going to be equal to PV over nR. We've got all those values, so it's 332 Kelvin, which is 59 degrees Celsius. The next question says 0.24 moles of gas is contained in a cylinder as represented. The gas is trapped by a disc of negligible mass so that the pressure in the cylinder is equal to the atmospheric pressure outside the cylinder. The disc can move up and down the cylinder without friction. Use the data to show that the length is approximately 1.2 meters, assume ideal gas behavior and explain your reasoning. So pause the video now, then unpause the video when you want to go through your answer. Right, in this question, how do you work it through? Well, we can work out what the volume is because it's 5 times 10 to the minus 3, which is going to give you your area times by the length. We know PV equals nRT, so therefore we can substitute that volume into that equation of PV equals nRT. Pop it in, and then you got your values for N, R, and T. Remember, temperature is in Kelvin, okay? And then we've got pressure given as well, so you can pop them all through to get L to be equal 1.19 meters. The next question says, an airbag is a safety feature used in cars. Nitrogen gas is released into an airbag. The airbag inflates to a volume of 7.08 times 10 to the minus 2 meters cubed. The pressure of the inflated airbag is 1.24 times 10 to the 5 pascals. Show that the number of molecules of nitrogen gas released into the airbag is about 2 times 10 to the 24. Nitrogen gas escapes from small holes in the inflated airbag. The pressure is decreased to 3.45 times 10 to the 4 pascals. Calculate the number of nitrogen molecules that escape from this airbag. The volume and temperature remain constant. So pause the video now, then unpause the video when you want to go through your answer. Right, we know PV equals big N KT, so therefore N is going to be equal to PV over KT. Pop in all the values. Now again, remember that we work our temperature out in Kelvin, not degrees Celsius. So pop on all the values and you get 2.13 times 10 to the 24. We can therefore say for this next question that because we know the volume and temperature remain constant, well then the pressure is directly proportional to the number of nitrogen molecules in the bag. So therefore P2 over P1 equals N2 over N1. So you can work out what N2 is, pop in all the values, and we get N2 to be 5.93 times 10 to the 23 is the number of molecules. But it wants to know how many molecules have left the bag. So you do the start number, 2.13 times 10 to the 24, minus the final number, 5.93 times 10 to the 23. So 1.54 times 10 to the 24 molecules have left the bag. In the next question, a toy rocket is made from a 1.5 litre plastic bottles with fins attached for stability. The bottle initially contains 0.30 litres of water, leaving 1.2 litres of trapped air at a temperature of 70 degrees Celsius. A pump is used to increase the pressure of the air within the plastic bottle to 2.4 times 10 to the 5 pascals at the start of liftoff. Figure 1 shows the rocket at the start of the liftoff. Calculate in moles the number of trapped air amount of trapped air in the bottle at the start of liftoff. The trapped air pushes the water downwards out of the hole, causing the rockets to rise. The temperature of this air remains constant. Calculate the final pressure of the trapped air just before all the water has been released. Use the data on the toy rocket to show that the upwards force on the rocket at the start of liftoff is about 15 meters, and then hence the initial vertical acceleration of the rocket. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we know N equals PV over RT. Pop in all the values. Remember, T is in Kelvin, so it's 0.12 moles. We also know from Boyle's law that PV equals a constant, or P1V1 equals P2V2. Pop in all the values, and P equals 1.92 times 10 to the 5 pascals. Now also we can know that the change in pressure is going to be equal to 2.4 times 10 to the 5 minus 1 times 10 to the 5, so it's 1.4 times 10 to the 5 pascals from the information given. We know that force is equal to the change in pressure times by the area, because pressure equals force over area. So you can work that through. You've got the area, so you get 15 newtons. And then finally, what's the initial vertical acceleration of the rocket? Well, the total mass of the rocket is 0.35 kilograms. F equals ma, where F is going to be the resultant force, which is the upwards force minus the weight downwards. So you can work it all through and you get A to be 34 meters per second squared. The next question says, calculate the average speed of the helium molecules at room temperature and pressure. Comment on how this speed compares to the average speed of air molecules at the same temperature and pressure. Then a sample of neon is contained in a cylinder at 27 degrees Celsius. Its temperature is raised to 243 degrees Celsius. Calculate the kinetic energy of the neon atoms at 27 degrees Celsius, 243 degrees Celsius, and compare the speeds of the molecules at the two temperatures. So pause the video now, then unpause the video when you want to go through your answer. Right, we know that P equals 1/3 P times by C squared, so you can pop in all the values and you get the speed out to be 1.69 times 10 to the 6, which when square rooted is 1,350 meters per second. Now, that's considerably faster than air molecules at the same pressure, because helium has this much smaller mass, so to have the same kinetic energy, which is the same for the same temperature, they've got to have a much greater speed. Now, in this next one, we know that the kinetic energy is 3 over 2 kT, so we do 3 over 2 times by K times by 300, the temperature in Kelvin, so it's 6.2 times 10 to the minus 21 joules. Do the same at 243, but remember now we convert our temperature into Kelvin, so it's 1.0 times 10 to the minus 20 joules. Now the ratio of speeds is going to be 1.07 over 0.62 by looking at the two values given before, so therefore the ratio of energies is 1.72. We know that speed links into energy by a square root because it's a half mv squared, so therefore it's going to be 1.31 to 1. The next question says, a truck is used to cross the Sahara Desert. The journey begins just before dawn when the temperature is 3 degrees. The volume of air held in the tyre is 1.50. It exerts a pressure on the tyre walls. Calculate the number of moles of air in the tyre. By midday, the temperature has risen to 42 degrees Celsius. Calculate the pressure in the tyre at this new temperature. You may assume that no air escapes and the volume of the tyre is unchanged. Calculate the increase in the average kinetic energy of an air molecule due to this temperature rise. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this question, how do you answer it? Well, in this first one, you can see that exerts a pressure by the kinetic theory as the molecules hit the wall and rebound from the wall. Each impact causes a small force or change in momentum and impulse on the wall. So the molecules are in random motion, so the more impacts will smear the force over the whole wall. Now the number of moles, we can say, well, ideal gas equation, PV equals nRT, N equals PV over RT. Again, remember, temperature should be in Kelvin, not in degrees Celsius, so we get 224 moles. Again, we can use PV equals nRT, so P equals nRT over V. Pop in all the values. T is in Kelvin, not in degrees Celsius, so it's 3.91 times 10 to the 5 pascals. We also know that kinetic energy is 3 over 2 kT, where the change in energy will be the change in temperature, so therefore you can pop it all through, and remember it's the change in the kinetic, the temperature in Kelvin, so therefore it's 8.01 times by 10 to the minus 22 joules. The next question says, explain what is meant by Brownian motion and how it provides evidence for the existence of molecules. The density of air at room temperature and pressure is 1.21 kilograms per meter cubed. Calculate the average speed of air molecules at this room temperature. State and explain the effect on the average speed of the air molecules of raising the temperature of the air going to a higher altitude but keeping the temperature constant. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, Brownian motion is the random zigzag motion of larger particles. So the air or water molecules will collide with these bigger particles. Each collision gives the larger particle a change in momentum or an impulse which will make it move in a different direction. This next one we can do P equals 1/3 PV c squared, so you can pop in all the values and you get 2.55 times 10 to the 5 as your c squared, so therefore c is equal to 505 meters per second. If you raise the temperature, well, temperature is directly proportional to the kinetic energy, so the speed will increase. Now going to a higher altitude, the speed will be unchanged because you're not actually changing the energy of the particles when you have a higher altitude because the temperature is remaining constant. The next question says, a student placed a metal block of mass 220 grams in boiling water at 100 degrees Celsius for several minutes. The student then transferred the metal block into 300 grams of water at 90 degrees Celsius inside a glass container of mass 50 grams. The final temperature of the water was 23 degrees Celsius. The table shows specific heat capacity values for copper and tin. Deduce whether the metal block was made from copper or tin. So pause the video now, then unpause the video when you want to go through your answer. Right, so the energy lost by the block is the energy gained by the water in the glass. So E equals mc times by change in temperature. So it's the mass, which is 0.22 kilograms, going from grams into kilograms, times by C, times by that change in temperature. So you can work it all through, and then you can see that actually you can then link it into the energy gained by the water and by the glass. So it's 0.05 times by 840 times by 4 plus 0.3 times by 4,200 times by 4. So we can write an equation out and say 16.94 C is going to be equal to 5,208 joules, so therefore C is going to equal to 307 joules per kilogram per Kelvin. So as you can see from the previous table, as it is 307, the answer is going to be copper. The next question says, an electric kettle contains 4.25 times 10 to the minus 4 meters cubed of water. The temperature of the water is 22 degrees Celsius. The kettle is switched on. The water takes 85 seconds to reach a temperature of 100 degrees Celsius. Show that the power of the kettle is about 1,600 watts. Then the water boils at 100 degrees Celsius. Calculate the time now taken for 75% of the water to boil away. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we can work out the mass because we've got the density, we've got the volume. So mass equals volume times by density, so it's 0.424 kilograms. We know that the change in energy, because it's change in temperature, is mc times by change in temperature. So therefore it's 0.44 times by 4,190 times by the change in temperature, which is going to be 78. So we get 1.386 times by 10 to the 5 joules. Power is change in energy over change in time. We know the time is 85 seconds, so it's 1,631 watts. watts. In this next one, because we're boiling, we're changing state. So now we say the change in energy is equal to the change in mass times by the latent heat capacity. So you pop in all the values and you get energy to be equal to 7.19 times 10 to 5 joules. Now again, you can remember that it's taking the time for 75% of the water to boil away. So if you noticed, okay, we can work it through that way because we've taken 75% of the water from the previous question. So we've done 0.75 times by 0.424. Now time is the change in energy over the power, so you pop it all through and you get 441 seconds. The next question says, a student investigated the relationship between the pressure and the volume of a fixed mass of gas at a constant temperature. He used his data to plot the following graph. The student stated his graph demonstrated that the pressure exerted by the gas was inversely proportional to the volume occupied by the gas. Assess the validity of the student's statement. So pause the video now, then unpause the video and you want to go through your answer. Right, so what you want to do is, if they are in fact inversely proportional, you should be multiplying the values of the y-axis and the x-axis, so find the points where they intersect, the coordinates of the line, and then they should all equal the same value. So again, when p equals 110, v equals 0.006, so you can times together at 660. Next, further down, when p equals 60, where v equals 0.011, so therefore it's 660 again. And then when p equals 51, v equals 0.013, multiply them together, 663. So the value of the two numbers as a product is constant, so therefore inversely proportionality is proven. That again, you should be doing at least 3 values to show that. The next question says, a sealed container contains n moles of an ideal gas. The gas has a pressure P, an absolute temperature T, and occupies a volume V. The mass of 1 mole of the gas is big M. Use the ideal gas equation to show that the density of the gas is given by the expression ρ equals Pm over RT. An airship has a cabin suspended underneath a gas bag inflated with helium. The airship is floating above the ground and is stationary. The volume of the gas bag is 12,000 meters cubed. The temperature of helium in the surrounding air is 20 degrees Celsius. The atmospheric pressure is 1 times 10 to 5 pascals. The molar mass of air is 0.029 kilograms per mole. The volume of the cabin is negligible compared to the volume of the gas bag. Show that the density of air under the conditions described is about 1.2 kilograms per meter cubed. Calculate the weight of air displaced by the airship. Explain why the weight of the air displaced by the airship has the same magnitude as the weight of the airship and its contents. And the pressure of helium in the gas bag is maintained at a value only slightly greater than the atmospheric pressure. Suggests why a larger pressure is not used. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this first one, we can say ideal gas equation, PV equals nRT. The mass is the number of molecules times by, so the number of moles times by the number of molecules in there. So therefore, we can substitute in the equation, cancel them all through, and we'll get ρ equals Pm over RT. In the next one, we can then work it through using the equation. So we can say 100,000, because we're converting kilopascals into pascals, times by 0.029, which is the molar mass. Okay, then divide by 8.31 times by 293. Temperature goes into Kelvin, so 1.12 kilograms per meter cubed. The mass of the air is going to be the density times by the volume, so you can work it through that way, as you can see in there. And then you can change that into a weight by times and by G, 9.81, so therefore we get 140,000 newtons. In the next one, we know that when something is floating in the air, the upthrust will equal to the weight of the fluid or the air that are displaced. So therefore the airship is in equilibrium. We can tell that from the information given in the question. So therefore the resultant force is 0. So the upthrust must equal the weight of the airship. And then finally, in the last one, the greater pressure would increase the density or the weight of the helium. And increased pressure but no change in volume would therefore have no more upthrust. So if the volume does go up, then the upthrust would increase. Now the pressure only does need to be large enough to inflate the gas bag, and an increased pressure may then cause a structural failure in the actual component with that increased pressure. So that brings an end to our revision session today. So hopefully, if you've been successful, you can answer A-level physics examination style questions for thermal physics. You can assess your understanding on A-level physics, and you can understand what topics need to improve upon for A-level physics in the thermal physics topic. So thank you so much for attending this revision session for AQA A-level physics on thermal physics. Thank you so much and have a lovely day. Hello and welcome to this revision session on thermal physics, which is part of the AQA A-Level Physics qualification. So in today's revision session we're going to look at answering examination questions for thermal physics. So if we've been successful and we've learned in this revision session, we should be able to answer A-Level Physics examination style questions, assess our understanding on A-Level Physics, and then understand what topics we need to improve upon for A-Level Physics. So how can we prepare in this revision session? Well, when completing your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side, and in this left hand side section write down your working out and answers to the questions in the revision session. Now when you're doing this, make sure you write out your answers in full sentences and show your working out. Whilst on the right hand side, write down any piece of information which you find useful or any hints and tips on answering questions from this revision session. And at the end of the revision session, write up these notes into a revision sheet for you to use independently. Now, what are the tips on how to revise for A-Level Physics? So first step is to learn the key facts. So use your revision guides, class workbooks, prep notes and textbooks to learn the key ideas of the course. Now you might wish to write out notes yourself or make mind maps. Second step is to test yourself. So use things like Caboodle, Seneca, the student knowledge checker to quickly test your own knowledge, and you may wish to do this from your own cue cards. And then the third step is practicing examination style questions. So using exam prep books, homework books, supervised study books, additional workbooks to answer exam questions and mark your own work. And you may wish to download your own exam past papers to do this. So the three steps of learning the key facts, then testing yourself, and then practicing exam style questions are the way forward for revising A-Level Physics. So let's start off by practicing a few multiple choice questions. So in this first question, at absolute zero an ideal gas will do what? So pause the video now, then unpause the video when you want to go through your answer. Right, so we've got to understand what absolute zero is. Now at absolute zero, a gas has no kinetic energy because the gas particles have stopped moving. It only has potential energy. So the gas particles do not move and will collide with the container they're in. So as such, they won't have any pressure because pressure is caused by the collisions of the gas particles with the container that they're in. So our answer is B. Next question. A student plans an experiment to test Charles' law for a gas. Which quantity of the gas must be measured and which must be kept constant? So pause the video now, then unpause the video when you want to go through your answer. Right, so in this one we've got to consider what Charles' law is. And Charles' law is the law linking the volume and the temperature. As such, they must be measured whilst the pressure and the mass are variables which we need to control to gain valid results because they can affect the values of a gas. So therefore our answer is C. Next question, which process will increase the kinetic energies of the particles involved? So pause the video now, then unpause the video when you want to go through your answer. Now it's important to note that what will happen here. So the answer is going to be B, because if you think about it, boiling and melting, options A and D are going to change the potential energy because you're changing the state. So we've got two options here, compressing the gas or expanding the gas. Now when you compress the gas, you are putting work into the gas to compress it, so therefore the overall internal energy of the gas must be increasing. So because we're not changing the state, we're just compressing the gas, it must be the kinetic energy store of the gas that's changing, so therefore it's going up. So our answer is B. The next question, when an ideal gas at temperature of 27 degrees Celsius is suddenly compressed to 1/4 of its volume and the pressure is increased by a factor of 7, what's the new temperature of the gas? So pause the video now, then unpause the video when you want to go through your answer. Right, the first thing we've got to be aware of is what's our equation for an ideal gas. So we know that PV is equal to nRT. Now we know that the pressure is increased by a factor of 7 and the volumes decreased by a factor of a fourth, so it's gone down to 1/4. So overall PV has changed by 1.75, 7 times by 1/4. Now as N and R are constant, if the left hand side has gone up by 1.75, the right hand side has gone up by 1.75, but N and R are constant, so only T can change by 1.75 to go up in that direct proportion as the equation suggests. Now it's important to note that this equation PV equals nRT is for when T is in Kelvin, not degrees Celsius. So you've got to convert 27 degrees Celsius into 300 Kelvin, and then we multiply that by 1.75, which is 525 Kelvin, and then turn that back into degrees Celsius by minus 273 from that. So our answer is 252 degrees Celsius, which is the answer of D. The next question. Which statement is true about an experiment where Brownian motion is demonstrated using smoke particles in air? So pause the video now, then unpause the video when you want to go through your answer. Right, so again, we've got to understand what Brownian motion is showing us and what the effect is demonstrating. Now the answer is C, because Brownian motion indicated that gases were made out of air particles, and the air particles moved in a random motion. Now this was indicated as the air particles collided with the smoke particles and therefore caused the smoke particles to move randomly because they're being hit randomly by the air particles. And we could observe the smoke particles moving randomly and then work out that air particles existed. So the answer was C. Let's have a look now at a few longer questions in thermal physics. So the first question is that nitrogen is heated from 70 Kelvin and is completely turned into a gas after 890 seconds. Calculate the specific heat capacity of liquid nitrogen and give an appropriate unit for your answer. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do we answer this particular question? So we've got to understand how much energy is being completely supplied to the nitrogen. So we've got to understand that the total energy supplied is going to be 12 times by 890. So therefore, we can know that it's 10,680 joules being supplied to change this. But we also know that the latent heat of vaporization for nitrogen is therefore going to be 2 times 10 to the 5. So we then work out the energy needed to evaporate it at its boiling point, which is going to be 0.05, because that's how much mass in kilograms you have of nitrogen, times by 2 times 10 to the 5. So therefore we can subtract that from our value. So therefore we can say that E is equal to MC triangle T. So therefore C is equal to E over M triangle T. The energy is going to be the total energy minus the energy needed to change the state. Then we divide that by the mass times by our change in temperature. So we get 1.9 times 10 to the 3. Now what's the units of specific heat capacity? It's joules per kilogram degrees Celsius or joules per kilogram Kelvin, which is an important idea. Now, let's have a look at our next question. So the work done by the nitrogen in the cylinder when expanding due to a change of state is X. The energy required to change the state of nitrogen from a liquid to a gas is Y. So deduce which is going to be greater, X or Y. So pause the video now, then unpause the video when you want to go through your answer. Right, so you've got to use this idea of volume is going to be mass over density, and you can see the density of liquid nitrogen and the density of nitrogen gas. So what you would do is, we know that that nitrogen for each of them has a mass of 0.050. Actually, it doesn't make a difference which one, what mass you use, because we say it's the same value for each one, will cancel through. So you work out how much nitrogen gas you'll need in volume, then you work out how much nitrogen liquid you would need in volume. Now at that point the work done is therefore going to be P times by the change in volume. So therefore we'll note that the pressure, which we knew before was 1 times 10 to the 5 multiplied by the work done, so you can work out that it's going to be larger for the liquid, because it's going to be a greater change in volume. Right, next question. State what is meant by the internal energy of a gas, and an absolute zero of temperature can be interpreted in terms of the ideal gas laws or the kinetic energy of particles in an ideal gas. Describe these two interpretations of absolute zero of temperature. So pause the video now, then unpause the video when you want to go through your answer. Right, so you've got to just learn these definitions. So what's the internal energy of a gas? It's the sum or the total of all the energy stores in a particle or atom or molecule. So you've got both the kinetic energy store and the kinetic and the potential energy store. Now because it is a gas, you would say that obviously you've got to say the kinetic energy of the gas itself. Now the second one is the interpretation of absolute zero. So it's important that you understand that it is in the gas laws, it's the temperature in which the volume or pressure of a gas extrapolates to zero. So you would note that it's the point for a gas in the gas laws that when it does not exert pressure anymore. So you could say that when PV equals nRT, it's the temperature where PV or V or P is zero because they'll link through, or when you plot a graph of volume against temperature, it's where it crosses the temperature axis, okay, where the volume will equal zero. Now the second interpretation is the particle interpretation of this, and that's using the idea that the kinetic energy is the temperature, it links to the temperature, so therefore it's going to be when the kinetic energy of the particles is zero, because at absolute zero the particles stop moving. Let's have a look at our next question. A mixture of argon atoms and helium atoms in a cylinder is enclosed with a piston. The mixture is at a temperature of 310 Kelvin. Calculate the root mean square speed of the argon atoms in the mixture, then compare the mean kinetic energy of the argon atoms and the helium atoms in the mixture. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do we answer this first particular question? Well, the first thing we've got to note is we're given the molar mass of the argon. So what we can therefore do is we can therefore work out the mass of one argon atom. So to work out the mass of one argon atom, we would do the molar mass, which we're given, divided by Na, which is Avogadro's constant, which is 6.023 times 10 to 23. So therefore, the first thing we do is we work out that the mass of one argon atom is 6.6 times 10 to the minus 26 kilograms. We can then work out the root mean squared speed by using our equation, a half mc squared equals 3 over 2 kt. We can then rearrange it to work out what CRMS is. So CRMS is 3 kt over m to the power of a half, or square root, it's the same thing. So we pop our values in. Now 3 obviously is just a number, K is a constant found in the equation book, T is the temperature in Kelvin, which we know from the question is 310. We can then divide that by the mass of one atom. Now remember, because a half mc squared links into the mass of the atom, not the overall substance, and then we square root and get 440 meters per second. Now the next question is comparing the values. Now the important thing to note is, okay, that it says in the question that the argon atoms and the helium atoms are enclosed in the cylinder and the mixture has a temperature of 310 Kelvin. So that's important to note that because they've both got the same temperature, both gases will have the same or mean average kinetic energy. Now they might not be moving at the same speed because it's a half mc squared, so therefore if one mass is higher, the value of c squared is going to be lower, but they will have the same kinetic energy if they're at the same temperature. Now the next question says, explain in terms of the kinetic theory model why a pressure is exerted by a gas on the piston. So pause the video now, then unpause the video when you want to go through your answer. Right, you've got to be aware of how pressure works in the kinetic theory model. So particles or molecules or atoms will collide with the container, the piston, the wall, and there'll be a change in momentum. Now how do you know there's a change in momentum? It's because there's change in direction. So there will always be a change in momentum. Now we've got to understand that force is the rate of change of momentum. That's Newton's second law of motion. So we can therefore say that we're going to have a force on the piston because the momentum of the gas particles has changed. So therefore we can say pressure is force divided by area, so therefore we can know that there's a force there, there's an area of the piston, so you can work out our pressure. Next question. The mixture of gases in the cylinder stays the same. Explain, using the kinetic theory model, two changes that can be made independently to reduce the pressure exerted by the gas. So pause the video now, then unpause the video when you want to go through your answer. Right. So how can you reduce the pressure exerted by the gas? So the first way you can do this, if you think of the kinetic theory model, that pressure is caused by the collision of the gas particles with the container, is you can increase the volume. Because if you increase the volume, it will increase the time between collisions, between the gas particles hitting the side of the container, or you could say that there's less frequent collisions. So therefore, you could argue that therefore the pressure is going to go down, or you could say that it'll increase increase the area of the piston in the wall, so therefore even if the force stays the same, the area gets bigger, so the pressure goes down. The second way in which you can reduce your pressure is by decreasing the temperature, because if you decrease the temperature, you're decreasing the speed at which the particles are moving at, because temperature links with average kinetic energy of the particles, so therefore there'll be a reduction in momentum, so therefore a reduction in the change of momentum, because if the values go from plus to minus and it's a smaller number, you're going to have a smaller change, so therefore our pressure produced is going to be smaller. Or you could also say, quite rightly, that if the temperature goes down, well then the particles are travelling slower, so there's less frequent collisions as well. So both ways will reduce the pressure exerted by the gas. Next question. A perfectly insulated flask contains a sample of metal M at temperature minus 10 degrees Celsius. Figure 1 shows how the temperature of the sample changes when the energy is transferred to it at a constant rate of 35 watts. Firstly, explain how the energy transferred to the sample changes the arrangement of the atoms during the time interval TA to TB. And then state what happens to the potential energy of the atoms and to the kinetic energy of the atoms during the time interval A to B. So pause the video now, then unpause the video when you want to go through your answer. Right, it's important to note that in time A to B, we're going to be changing the state. Now, it's important to note this because you can tell that the temperature itself is not changing, so any energy is going into changing the state. So therefore, the energy is transferred to though the atoms move the center of their vibration or they break some of their atomic bonds. So therefore, if you look on here, from A to B, the atoms are moving further apart. So what's going to the potential energy and the kinetic energy? Well, it's important to note that the kinetic energy remains constant. So it's important to note this because if we note on this idea, okay, that the kinetic energy is constant because the temperature, which is a representation of kinetic energy, stays the same. But the potential energy increases. How do we know that? Because it's a flat line, so there must be a change in state. And because we're heating it up, we're putting temperature into it. So we're putting energy into it, sorry. So therefore, the potential energy increases. The next question says, the sample has a mass of 0.25 kilograms. Determine the specific heat capacity of M when in the liquid state and then state an appropriate SI unit for your answer. Now to help with this one, you might want to go back and just look at the graph again here, okay, to see if you can get some values from the graph which will help you derive the specific heat capacity. Right, so pause the video now, then unpause the video when you want to go through your answer. Right, so it's important to note that we know that the equation for heat capacity is E is equal to MC triangle T, or else MC delta theta. Either way, it's fine. Now to work out our energy or our change in energy, it's going to be power times by time. So what do we know? We know that the power from the previous question we looked at, it says that we've got a constant rate of 35 watts. Okay, so we know that we've got 35 watts there. We can see on the graph how long it takes to change when it's in its liquid state, so we can work out the time there. Now note we work in seconds, so you've got to change it into seconds here. Then we divide it by the mass, which is given in the question with 0.25, multiplied by the change in temperature. Once again, this change in temperature is given on the graph. So we're starting at, if we have a look on here, we're starting at 28 degrees and we're going to, I believe, 112, so you can work it through like that, and you've got your time, but obviously converted into seconds as well. So therefore you can work it through to get 370. Now again, what's the unit of specific heat capacity? It's joules per Kelvin degree Celsius, or joules per Kelvin, sorry, kilogram Kelvin. So it's joules per kilogram Kelvin, or joules per kilogram degree Celsius. Sorry about that. The next question says, Table 1 shows the specific latent heats of fusion L for elements that are liquid at similar temperatures to M. M is known to be one of the elements in Table 1. Identify M. So remember again, what do we know? We've got our graph before, so if we look back on our graph to help us work these things through. So pause the video now and then unpause the video when you want to go through your answer. Right, so how would you do this? So we'd say L is going to be equal to the power times by the time over M. Why is that? Because we know E is equal to ML, and E is the power times by the time. Okay, and then we know what our mass is. So what we need to do is we know our mass is 0.25 kilograms. We know that our power was 35 watts because it told us previously in the question. We can go back on the graph and we can determine the time at which it changed state, because latent heat refers to change of state. So we know that it started changing state at, let's get this right, 1.8 minutes, and then changed at finished changing state at 11.2 minutes. So what we can therefore do is we can then look at that, we say 11.2 minus 1.8, but then we convert that into seconds, and we then times that by 35 to get our energy, divide by our mass is 0.25, so we get 79 kilojoules per kilogram. Now it's important to know that what's that close to? It's going to be gallium. And why is it slightly different? Well, there's going to be inaccuracies in the investigation, so it's not going to be exactly 80. Let's have a look at our next question. Helium gas particles are single atoms that behave as an ideal gas. A container of helium gas is used to inflate an empty balloon. Immediately after inflation, the gas in the balloon has a pressure of 106 kilopascals, a temperature of 288 Kelvin, a volume of 1.4 times 10 to the minus 2 meters cubed. So show that firstly the number of atoms in the balloon is approximately 3.7 times 10 to the 23, then that each helium atom has a mass of 6.6 times 10 to the minus 27 kilograms. So calculate the density of the gas in the balloon. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do we work this one out? Well, we can look in the back of our equation book and we know that we've got an equation which has a number of atoms in it, and that is PV is equal to NKT, where big N is equal to the number of particles in the substance. So we can then rearrange it and make N the subject. So we can say N is equal to PV over KT. We've got P, we've got V, we've got K because it's a constant, and we've got T. Now the only thing we've got to remember is it's 106 kilopascals, so we've got to change that kilo into just a normal value, so it's 106 times 10 to the 3. So we can put those all in and we get 3.73 times 10 to the 23. Now again, why do we give it to 3 sig fig? Because all the values given in the question are given to 3 significant figures. Now our next question is asking for the density of the gas in the balloon. Now what we need to do is we need to work out the total mass of the atoms in the balloon. So we know that there are 3.73 times 10 to the 23 atoms in the balloon. We know the mass of each atom is 6.6 times 10 to the minus 27. So we can therefore work out our total mass by doing that. We can then say density is mass divided by volume. Again, that equation is given to you in the back of your equation book. We know our volume because it's given in the start of the question, so we can work it out to be 0.18 kilograms per meter cubed. Next question. The rate of flow of water through a panel is 45 grams per second. The water enters the panel at a temperature of 15 degrees Celsius and absorbs energy from the panel at a rate of 1.7 kilowatts. Calculate the temperature of the water as it leaves the panel. So pause the video now, then unpause the video when you want to go through your answer. Right, so how would you answer this question? Well, again, you talk about heating something up. So we will use our equation E is equal to MC delta theta, or E equals MC triangle T. Now we know that we want to make the change, we want to work out the change in temperature. So we'd say that E is going to be equal to MC triangle T, so therefore triangle T or delta theta is equal to E over MC. We've got C, 4,200. We've got M. Now again, we'll take it over 1 second. So 45 grams per second becomes 45 grams. So we turn that into kilograms. We then know that 1.7 kilowatts in 1 second becomes 1.7 kilojoules, because a watt is 1 joule per second. So therefore we can say it's 1,700 divided by 0.045 times by 4,200. So therefore we get our value of our delta theta. Then we can add that onto our starting temperature to work out the temperature at the end to get it to be 24 degrees Celsius. Next question. The equation PV equals a third Nm C RMS squared applies to an ideal gas. The derivation of the equation depends on the assumptions made about the gas. State 2 of these assumptions. Then a sample of an ideal gas has a temperature of 12.5 degrees Celsius. The mass of each particle of this gas is 6.6 times 10 to the minus 26 kilograms. Calculate the root mean squared speed for the particles in the gas, given your answer to the appropriate number of significant figures. So pause the video now, then unpause the video when you want to go through your answer. Right, it's very important you know all the assumptions about an ideal gas. So the major ones regarding the gas itself are as follows. There's negligible forces between the particles. The volume of the particles is negligible compared to the volume of the container, so they're point masses. The particles collide elastically, and the collision duration is negligible. It doesn't exist compared to the time between the collisions. Like I said before, it's very important you just learn the assumptions of the ideal gases. Now the next one is we need to work out the CRMS. So what I would do is I'd look in the back of my equation book and I'll see I've got an equation which says a half mc squared is equal to 3 over 2 kT. Now from the information we've been given in the question, we've got m because that's the half mc RMS squared. M is the mass of one particle, so we can use that mass in our equation. We've got a temperature for 3 over 2 kT. Now again, K is a constant, so that's just a value. Now T has to be in Kelvin, so we change 12.5 degrees Celsius into Kelvin. We then pop the numbers into the equation, rearrange for CRMS, and we get our answer out to be 423 meters per second. Now again, how many sig figs should you give it to? So you should give it to two significant figures, because 6.6 times 10 to the minus 26 is one of the values given, and that's 2 sig fig. You might say, well, what about 12.5? Because that's 3 sig fig. Well, you always go with the lowest number of sig figs given in the values of a question. So 2 is smaller than 3, so you go with 2. Next question. A gas has a density of 12 kilograms per meter cubed when its temperature is 860 Kelvin and its pressure is 2.1 times 10 to the 7 pascals. Show that 60 kilograms of a gas contains approximately 9 times 10 to the 27 particles. Calculate the molar mass of the gas and then state an appropriate unit for your answer. So pause the video now, then unpause the video when you want to go through your answer. Right, so in this first one, we need to look at, we've got density and we've got pressure, so we then need to think about our volume. So we can say that density is mass over volume, so therefore we can use that to then work out our volume by doing volume is mass over density. So we've got our mass is 60 kilograms, we've got our density is 12 kilograms per meter cubed, so therefore, there's our density, so therefore we can work out the volume. We can then say PV is then equal to nRT, or I would actually do PV equals big N KT, where N is the number of particles. We then make a big N the subject. We say big N is equal to PV over KT. We've got T at 860 Kelvin. We've just worked out what V is. We've been given P in the question, 2.1 times 10 to the 7 pascals. K is a constant, so therefore we can work out big N to be 8.8 times 10 to the 27. Then calculate the molar mass. Well, we know that the molar mass, we can have the molar mass is because we're going to say that the mass is going to be equal to the number of moles times by the Avogadro constant. So what you can therefore do is therefore you can say that M over N will give you your molar mass. So therefore we can work it through like that to get 4 grams per mole. Next question. The gas is heated at a rate of 75 megawatts as it flows through a pipe. A mass of 60 kilograms of gas flows through the pipe each second. The gas enters the pipe at a temperature of 860 Kelvin. Calculate the temperature of the gas as it leaves the pipe. So pause the video now, then unpause the video when you want to go through your answer. Right, again, we've got to use our equation that E equals MC triangle T, or E equals MC delta theta. So what we can therefore say is we can say that if we take it over 1 second, we can turn our 75 megawatts into 75 megajoules, and we've got our mass to be 60 kilograms, because this is 60 kilograms every second, so take it per second. So therefore we can say that 75 times by 10 to the 6 equals our 60, our mass, times by our heat capacity, which is 4.9 times 10 to the 3, times by our change in temperature. We can therefore work out what our change in temperature is. We can then add that to the starting temperature, which is 860, to get our temperature at the end, which is going to be about 1100 Kelvin. Then here's our next question. The temperature of the helium in the balloon changes from 25 degrees to minus 50 degrees during the balloon's ascent. Calculate the change in internal energy of the helium. 1 mole of helium has a mass of 4 grams. So pause the video now, then unpause the video when you want to go through the answer. Right, so how can you work this through? Well, firstly, what do we know? We've been given in this question the change in temperature. Now we know the change in temperature is 75 degrees Celsius because it's gone from 25 degrees Celsius to minus 50 degrees Celsius. So the change is 75 degrees Celsius or Kelvin because they're interchangeable at this point. How many moles do we have? Well, we know that we've got 1 mole of helium is 4 grams, and we know from our previous question that we've got 60 kilograms. So we can therefore work out we've got 145 moles of the helium. Therefore, we can use our equation 3 over 2 nRT to work out our value, because we've got T to be 75, we've got R, which is a constant, and we've got N to be 145 moles. So you can pop those all in and we get 1.35 times 10 to the 5 joules. And this is a minus value because the number's gone down, it's cooling down. Our next question says that for this balloon, the same balloon expands as it ascends. The temperature inside the balloon is always greater than the temperature outside the balloon. Explain by using the first law of thermodynamics how the internal energy of the helium changes during the ascent. So pause the video now, then unpause the video when you want to go through your answer. Right, you've got to be aware of how we can use the first law of thermodynamics. Now, the important thing to note is the helium does work in expanding. So when the actual gas expands, because it says it's expanding, heat is being transferred from the balloon to the surroundings because the balloon's at the higher temperature. So it's important to note that both Q and W are negative, so the internal energy falls. So why is delta Q a negative? Well, energy is being lost to the surroundings because the energy will always flow. The kinetic energy of the gas will always flow from the high temperature to the low temperature. So the higher temperature is inside the balloon. It's the gas inside the balloon. So that's losing the kinetic energy to the outside because the outside is the lower temperature. And also, in addition to that, the potential energy is going down as well, because what's happening is that as it's expanding, work is being lost out to the surroundings, because when you compress a gas, work is done into the gas, while when a gas expands, work is done out of the gas to the surroundings. So you're losing energy both from the temperature and from the fact it's expanding, so therefore the internal energy of the gas is going down. So I hope you've enjoyed this particular revision session. So if we've been successful and we've learned in this revision session, we should be able to answer A-level physics examination style questions, assess our understanding on A-level physics, and then understand what topics we need to improve upon for A-level physics. So I hope you've enjoyed this revision session on thermal physics, which is part of the AQA A-Level Physics course. Thank you very much for listening and watching. Have a lovely day.